First one is things to get right in order of importance for model simulations. So we were thinking about large-scale flow, jet streams, storm tracks, and topography are important. And the second important one is the eddy and the mean flow interactions. So the third one we were thinking is the diabatic heating. And within diabatic heating, we were thinking about latent heating and warm conveyor belt. The second most important is ocean surface fluxes. After that, we did not get an agreement on which one is more important. So we would say clouds, boundary layer, land surface fluxes are in similar importance. And then we were talking about what do models struggling with. So we think the first thing is model is in lacking of resolution, both horizontally and vertically. And we were talking about small biases in large scale flow can have big impacts on certain blocking metrics. Also, models are struggling with convection parameterization and ocean atmosphere coupling. Also, models currently cannot resolve topographic gravity waves and also cloud radiative effects. We go to next slide. Then we talk about the ideas for maps. So we were talking about if we can have initialized prediction of different case studies at different resolutions, from relatively larger to really fine resolution. So we can have a range of blocking types during different seasons over different locations with large ensemble members for each of the case study. And that can allow us for a systematic investigation into the impacts of resolution on blocking representations. Also, we're wondering if we can getting the weather model group and the climate model group together to do an intercomparison between weather operational models and climate models for subseasonal and seasonal prediction to see if we can help each other understand the theory and also model simulations better. We're also wondering if it's possible to use one or several weather operational models running for a longer time period to see if climate models can learn something from the weather models. We were also thinking if we can have like a hierarchical modeling, such as, so we were thinking if there are some models that already exist from more idealized, say idealized topography or like slab ocean, to examine what are the main factors for the blocking simulation. And we're also thinking maybe we can build a set of model from very idealized settings, adding more and more processes to test how to simulate blockings better. That's the end of group one's discussion.
Thank you, Xiaoyi. Group two.
Okay, start out our session. I decided to be a little provocative and talk about omega blocks and Rex blocks, and does it really matter which one is which? And I would like just to make the point that when you talk about something that's quasi-stationary for like 3, 4, 5, 6, 7 days, the trajectories coincide with the streamlines more carefully. So they're not to scale, but when you have the Rex block, I mean the omega block on the left, air comes from further south. Whereas in the Rex block, the high over the low, it's hard to get air to pass, to go through a substantial change in latitude compared to the omega block. So the omega block, if it lasts like, say, 5, 6 days, has the potential to allow very warm air from lower latitudes to get poleward compared to the Rex block. That's a testable hypothesis that I think would be rather interesting. That would just rattle cages.
So I'm just going to briefly discuss the recap from the group 2 of the breakout session. And so this was the teaser given by Lance.
Could you be a little closer to the mic, please?
Okay, sorry. Thank you. Is it okay right now? Okay. Well, after this, we discussed there are different factors to be considering when it comes to extreme weather events. It needs to be looking at the location, the persistence, and other criteria that completely decides how extreme or severe the weather events can get. And after that, we looked into the perspective of blocking processes and how well or how moderately they're represented in the climate models. And we tried to rate them based on the scale of 1 to 5, that how well they do or how well they are represented in the models. So there is sea surface temperature gradient, wave dynamics and mean flow, synoptic eddy, topography, and stratospheric influences, where stratosphere influences could depend on the model, how the model is very well resolved in the upper levels. Then there is tropical convection. Apparently, convections is very well represented in the climate model these days. And then there is teleconnection and climate modes, which is apparently it's not very well captured by the today's models. And then there is diabatic processes, which comprises of the latent heating, radiative processes, ocean and air interaction, and there is something that is hidden down. Sorry about that. That is cloud effect. Well, these all are the very good processes that need to be incorporated in the climate models to very well or accurately capture blocking. Could you put the next slide, please? Well, some of the key points after doing this activity was put forward by the team, suggesting that accurate representation of blocking needs an accurate background state at first, but it is indeed a challenging task because it is tightly coupled with other smaller scale aspects and other things as well, including soil moisture feedback, diabatic processes, land-ocean coupling. And yeah, these all processes are very important when it comes to accurately capturing blocking as a whole. Well, important point was that teleconnections and the climate modes are not very well represented in the climate model, which is something to look forward. And from the machine learning perspective, so machine learning is in general will provide us a computationally less expensive pathways. And if they are doing better or comparatively good as compared to the climate models, we should really encourage and look into further details of that. Then there was also some discussion where there was a discussion suggesting that these machine learning model actually highlights a pathway for a better predictability. That means sometimes it gives a signal which are more pronounced in some parts, and that could help us to better predict blocking. Well, that was all. Thank you.
Right, thank you very much. Let's Vinta.
Hello, am I audible? Thanks. So my name is Prasad. I'm from Victoria University of Wellington, and I'll just briefly summarize what we discussed in breakout session group 3. First of all, knowledge gap for blocking representation. So on the basis of ratings, we agree that neither is terribly represented nor is very well in terms of blocking representation. And some processes or like discrepancies in model are highlighted over here. According to the ratings that we agree, like which one should be on the top. Almost everything is included. Specific emphasis we discussed on the drag, and I think moreover related to the mean state and cloud-related processes, which often parameterize. Next slide, please. Coming to diabatic processes, we agree that latent heating should be the top-ranked parameter in terms of diabatic processes, and followed by CRE, radiative heating, and soil moisture, which is one of the things that has been presented in just previous discussion as well. So under warming climate, are we expecting any changes? Yes, of course. That's what we discussed, and some prominent changes we should expect a shift in storm track and probably southward transport or southward migration of jet stream, which can enhance or affect the wave breaking perspective. Other thing, strengthening of mid-latitude jet, probably yes, related to changes in diabatic heating under warming climate. And would that result in decline in blocking? Yes, probably that's one of the reasons why we are projecting the decline in blocking in climate models as well. Blocking diversity, we just expect there should be different responses because of the changes in diabatic processes in future, and also for different blocking types as well. Next slide, please. Yeah, so coming to a very important point, we discussed about machine learning. So we discussed that it can help in like simulating parameterized processes well, because it's a black box. But it should be more useful in seasonal weather forecast, rather than probably if we want to adapt that approach for using with climate model, we should adapt some hybrid approach where we parameterize using machine learning and maybe simulate blocking in climate models with those parameterizations. Again, we go ahead and probably there was one discussion about if we embrace linear regression techniques and statistical methods a lot, why not to adapt ML? Like, there is no reason to avoid or like sideline the technique. About model intercomparison projects, we thought that we should embrace different techniques or different methodologies to track blocking. It shouldn't be overwhelming. It should actually be welcomed. But we agree that there should be some common protocol to compare the blocking representation in different climate models, or probably with weather models as well. And as usual, weather and climate community. So there has been discussion which like we probably reach on a point, will blocking a gateway to bridge the gap between weather and climate community or what. So yep, that's it. Thanks.
Yeah, thank you, Prasad.
So in our group, we also discussed a lot about the convection and topography, both of which are poorly simulated in climate models, but can effectively influence the block. And for example, for convection, the cloud and the related microphysics process is always a hard topic to parameterize in the models. And we also discussed some other factors like the mean flow and eddies. These two seem like is well simulated and is important for the dry dynamics of the blocks. We also talk about the influence of the stratosphere. So it seemed like we are wondering if a model can better resolve the stratosphere, like a high top model, than if it could better resolve the block. And there's some question in that there's actually, those factors are really tangled with each other. Sometimes it's really hard to disentangle the role of individual. For example, if we want to study the rule of like the horizontal resolution, and if you just increase the resolution, you will find that the topography is actually also well resolved, and which can effectively change the block. So yeah, these factors are tangled with each other and hard to study them separately. We also talk about the role of teleconnection, and I think this is complicated because it's connected to all these different factors, like the tropical forcing, MJO and ENSO can effectively influence the block. And the teleconnection also requires better and the teleconnection also requires a better simulation in the tropics diabite heating. If the diabite heating in tropics is not well simulated, then this teleconnection pathway may not work. As to the diabite heating specifically, we discussed that yeah, diabite heating is definitely will increase in the future, but if it can really play a role in the blocking life cycle, it's worth discussing. So we can just say that, yeah, in the future climate, the moisture is increased, the diabite heating is increased, then it definitely will play a more important role. We need to more carefully to think about this increased diabite heating. And also, we also need to consider the diabite heating in tropics, because by the teleconnection, it can also influence the block in the mid latitudes. Like here, next slide, please. Oh, sorry. And some idea is that like study the influence of improved the resolution with regard to topography with the physical parameterization, and use a high top model to look at the impact of stratosphere process. And yeah, we need more complex experiment, but it's better to start with aquaplanet simulation to try to understand the theory better. And also for the machine learning thing, we also discussed that it's important to know the science behind it. So for example, we need to use an explainable AI. We cannot just, yeah, we got the result and go. We need to understand the science behind it so that it can really prove the science community. I think that this is what we summarize. Thank you.
Yeah. Thank you, Joy.
So hi again, everyone. Good morning to all. I'm Pragalva Barpanda. I'm from the Geophysical Institute, University of Bergen, and the Bjerknes Center for Climate Research, Norway. So there are some, I think the rest of the groups covered most of the points that we discussed. I'll just add some additional points. There was a question about what are the open questions for the theory of blocking and what is the greatest disagreement. I think the broad consensus in our group was that there is no one comprehensive theory of blocking. And so obviously every theory is lacking and may not explain everything about blocking. And I think that's fine. For example, Nakamura's traffic jam theory tells us about the onset of a block. Yamasaki and Ito's selective absorption mechanism of paved blocks tells about the longevity of blocks or how long they are going to stay. And even for basic topics like cyclogenesis, we probably have more than one theory, just that baroclinic instability happens to be the more popular one. So the key point is that we do not necessarily need to have a universal theory, and maybe different theories can be useful to explain different aspects of blocking. So, but the key is that we need to find some convergence and treat them as different pieces of puzzle and find the limits where they work and where they don't, and try to utilize them as much as possible in these different regimes, wherever these theories apply to. There was another question about what are the important interactions between blocking and other components of the Earth system. And it seems like anything that impacts the atmospheric circulation is important for blocking. So, so we could not come up with a ranking, and we probably need a lot more studies like yesterday's Sandra Luby's talk on the cloud radiative effect and other idealized studies to really understand the importance of various sources. It seems like everything is important, but to find out the first order impacts, more idealized studies and blocking MIP is really important to find convergence there. Regarding the kind of experiments we would propose for modeling intercomparison projects for blocking is that we really need to think about whether we want to answer a question in a weather framework or in a climate framework. In a climate framework, one suggestion was that we could do something as simple as an aquaplanet intercomparison project like an AMIP, where we change very simple parameters as the zonal mean temperature gradient, the rotation rate of the planet, and answer some basic questions about how these basic parameters can influence the blocking statistics, and that can inform us a lot about how the blocks would change in climate change scenarios. In weather framework, one way to do is to think about as initial value ensemble runs and fix the initial condition and see how these different ensembles perform in terms of simulating blocks. But we would also highlight the importance of setting a particular set of diagnostics for all these blocking experiments. So whatever experiments we do, we also need to really come up with the protocol of these different diagnostics so we can find some convergence there. And to do that, we need a group of like a combination of blocking expert and modeling experts to come up with these suggestions of set of diagnostics. We also touched briefly about the question about the two perspectives of European and American school of thought, and how are these two perspectives similar or different. And so this is again a biased opinion based on very small number of people in a group. So the key agreement was that in America, it seems there is more schism between the weather and climate studies. In the climate studies, there seems to be some really nice groups pushing towards more and more idealized studies, which is very encouraging and should be encouraged further to do so. In Europe, there is less schism between weather and climate, and so perhaps less focus on idealized studies, but there is a lot of exchange of ideas between the weather and climate community, which is extremely important. So yeah, I think that's all.
Thank you very much.
We do have 10 minutes left before our next session. So I'm wondering if anyone has any thoughts about the discussion, what you found interesting or surprising, or have questions. Please feel free to come up to the mic.
Yeah, hi Jan. Something I hadn't actually thought about until last night. This this discussion about a MIP, whether a blocking MIP would be useful. A kind of a slightly different model for that kind of thing is what they're doing with the QBO intercomparison. So as part of Spark, which is now APARC, I guess, they have this something called QBOI, which it's not really, it's not a MIP in the sense that everybody does, it's not like a CMIP MIP where everyone does the same experiment. In a sense, it's kind of more of a long-running community, I think, where they do kind of do some experiments. They design some maybe small targeted experiments, but it's a lot more about kind of coordinated diagnostics, getting kind of groups together to to kind of share the load in a sense. And if you want to systematically, they systematically look at different aspects of the QBO in the same simulations using kind of a whole bunch of different diagnostics as kind of a bigger international team. So that might be a kind of a slightly different kind of setup in a sense than a MIP that might be worth considering if there is kind of interest in that kind of thing. So just have a look at QBOI, which is now on the APARC website.
Yeah, Tim, thanks for the comment. Yeah, this also reminds me of the talk about Serafin yesterday about the kind of Lagrangian perspective versus the O'Leary one. Yeah. Any more comments?
Ping, go ahead.
Yeah, thank you. In terms of the MIP, I have some thoughts about this. In addition, on top of the traditional MIPs, I think blocking MIP probably should focus more on the event-based MIPs, such as we had a lot of historical long-lasting blocking events in different types. And if we can select many of them and as a prototype, as a targets, we can either use the existing model products, including the reanalysis, and also future participating models to target on those specific events and focus more on those events in terms of onset, life cycle, dynamics, etc. But the point is, we probably should focus more on the event for these MIPs.
Right. Thank you, Ping. If no more, yeah, we'll transition to our first plenary session.
All right, good morning, everyone. I'm Stephanie Henderson from the University of Wisconsin-Madison, and I will be chairing this session along with Melissa Breeden. So this session will deal with interactions with other components of the Earth system, and we'll go ahead and begin with our invited speaker, who is Christina Karamperidou from the University of Hawaii.
Right, thank you very much. Thank you to the organizers. This has been really a wonderful workshop, and I appreciate the opportunity to give this presentation. I'll first present an overview of the relationships between atmospheric blocking and large-scale modes of climate variability, and then I will focus on the key role of the tropical Pacific, since this has been the work that I've been involved in. I think we all appreciate here, and especially after the last couple of days, how much of a wicked problem blocking is, in the sense that it is complex, it is nonlinear, sometimes we lack definitive formulations, and what we observe can accept multiple explanations, and this is kind of the definition of a wicked problem. And for better or worse, unfortunately, these large-scale climate variability modes and their interactions and impacts are similarly wicked problems. And some of their characteristics that do influence the relationship with blocking is, first of all, we have all these, they operate in these multiple timescales, from intraseasonal, like the MJO, and all the way to multi-decadal and centennial. That is part of the reason why establishing causal relationships can be pretty challenging. We also have tropical and extratropical patterns that can have opposing or concurring impacts on atmospheric circulation in the mid and high latitudes. And apart from the interaction between modes and blocking, we also have interaction between modes themselves. So we have all these interbasin relations and all this stuff. And of course, when we look to models, as we discussed a lot yesterday, to understand these relationships better, we are faced with the limitations and biases of the models. Nevertheless, the relationship between blocking and these large-scale modes of climate variability, it does offer opportunity for improved predictability. For example, Mingyu Park yesterday showed us how Niño 3.4 can help with more skillful predictions. And also they offer potential analogs between climate variability and change, albeit with caveats there. So I will start with one of the most maybe well-studied relationships within the North Atlantic Oscillation and blocking. So during positive NAO phase, we have more of this European blocking, and during negative NAO, we have a lot of Greenland blocking. So this anti-correlation between NAO in the solid line here and high latitude blocking, whose inverse you see in the dust line here, has implications for predictability. However, NAO and blocking have similar spatiotemporal scale, so the alternate view of this is to look at NAO variability as a result of variations of in high latitude blocking on interannual and longer time scales. So in this paper by Woolings et al., you see that the skewness of the NAO index has been can be explained by these two regimes, Greenland blocking and more of this subtropical jet situation. And of course, looking at model biases in NAO and model biases in blocking, they're very much connected or correlated. I do want to point out that the relationship may depend on the metric. Kayla Bison had a poster on Monday about the sensitivity of this relationship to the metrics used. A somewhat similar situation, we have the Pacific North American pattern. So the PNA, you see the tripole kind of pressure patterns associated with it here. And it is temporally and spatially correlated mainly with Pacific blocking. You see during PNA negative, much more Pacific blocking. Of course, the modulation of PNA and its impacts by ENSO has been discussed since a long time ago. And much like with NAO, you can look at atmospheric blocking as a major contributor to PNA variability. So for example, in this paper by Krotsimas-Poli et al., they discussed how blocking can sustain negative PNA from genesis to lysis. This is genesis in the dark circles here and lysis in the lighter circles, and even trigger a phase transition from neutral positive PNA to negative PNA. Now, maybe encompassing all of this is the Arctic Oscillation, or otherwise known as the Northern Hemisphere Annular Mode. So the anti-correlation here again between the AO index and blocking. And during AO negative, you see here for both DJF and JJA, the blue line is for AO negative cases. We have increased blocking by threefold compared to the positive AO phase and shifted to the poleward. This relationship between AO/NAO/PNA and blocking may pass through the sea ice variability, and we have some talks later about sea ice. And that has been, I guess, the background based on which AO negative has been discussed as a positive, as a potential analog for global warming or Arctic amplification. However, this is a challenging question. The mechanisms and causality and the analogs, they are quite tricky because there's a lot of players there and they can lead to opposite impacts on blocking. And that was actually the subject of this paper by Pedram Hassanzadeh and Kwang, whether AO negative is a valid analog for Arctic amplification. Right. I'll stick to the exotropics. So now longer timescales, the Atlantic multidecadal oscillation or variability, if you like, during positive AMO, so warmer temperatures here in the North Atlantic, we have more frequent NAO negative and more frequent Atlantic blocking. This is the darker box plots here. During AMO positive. The AMO blocking relationship has been shown to be stronger when the AMO or AMV leads the NAO in blocking. This is kind of the stronger correlation seen here when AMV is leading. At the same time, though, for example, in this paper by Hakkinen and al., the discussion was how more frequent blocking, this is the black line here, corresponds to a warmer, more saline subpolar ocean. So this is the AMO kind of index in the red line. And this is due to the forcing of the ocean gyre by the atmosphere and the persistent blocks. Also, if there is a connection between the Atlantic Meridional overturning circulation now and AMO. There has been also a work on AMOC shifts potentially triggered by blocking via changes in the sea ice export. We also have a talk later on AMOC in this session. So again, there's a possible two-way coupling between AMO/AMV and blocking. So things may be a little bit more clear if we go to the tropics, being that the mechanism of tropical influences to the extratropics, so this change in the heating source. So at the shorter timescales, interseasonal timescales, we have the Madden-Julian oscillation characterized by these dipole OLR anomalies here, the going around, characterized in 8 phases. And you can see associated with them, we have changes in how elongated or strong the jet stream is, and also changes in blocking. So in this figure from Henderson and al., you see that depending on the phase of the MJO and for different lags, you can have, and depending on the location, either decreased blocking or increased blocking compared to climatology, and that would be the black line here. So a lot of potential pathways, again, are associated with the impacts of MJO on NAO/AO/PNA, and there is a lot of literature on this aspect with, the interactions between the holy acronyms here. However, MJO events, they do vary in speed, intensity, and structure, and together with the sensitivity to initial state of the response of the extratropical atmosphere, this introduces uncertainties in this relationship, as with everything else. The other thing that's happening when you have MJO going around the globe is the other big player in the background in the tropical Pacific, and that would be the El Niño Southern Oscillation. So it's been known since a while now that during El Niño events, we have fewer and weaker blocking events over the Pacific. So this is kind of the frequency in shading here during El Niño and La Niña. Climatology, this DJF. Climatology is in the contours. And in the Southern Hemisphere, there is increased blocking during El Niño, and that has been associated with the increased variability of the South Pacific Convergence Zone, being that is the heating source for the extratropical wave trains. Now, in a lot of these studies, especially the recent one, it's often discussed that the ENSO signal is kind of found to be weak and mostly applying to the preferred blocking locations. So you see here in the difference, kind of more of a shift of where you have your climatological peak, but less of the change in occurrence, like frequency of blocking. And there could be many reasons for this. One of them is that, well, when you have ENSO happening in the background, you have yet another player, and that would be the multi-decadal state of the Pacific, one expression of which is the Pacific decadal oscillation, or variability, if you like. The warm pattern of this is shown here. It has this extratropical kind of horseshoe pattern of warm SSTs. It also has a tropical expression, which is more an El Niño-like kind of pattern. And in this table from Lupo, you see that the occurrence, duration, intensity, and concurrence of blocking in the North Hemisphere during El Niño, neutral, and La Niña events, it is kind of different depending on whether you're in a PDO positive phase or a PDO negative phase. So if you're in a negative phase, a more La Niña-like state, you have more of this increased, persistent, and concurrent total North Hemisphere blocking during El Niño events, whereas in a positive PDO phase, you have decreased blocking. In the Southern Hemisphere, there's increased Southern Hemisphere blocking during positive ENSO in both phases of the PDO. So Another reason why you can have an obscure maybe ENSO signal in blocking is because much like blocking, ENSO also comes in flavors, what we call ENSO diversity. So we can have Eastern Pacific El Nino events where your sea surface temperature anomalies are more in the East Pacific, and this is the kind of strong OLR anomalies in contours that go together with that. Or you can have Central Pacific events where the SST anomalies peak in the Central Pacific and collocated with weaker SST anomalies, OLR anomalies. So depending on the season and location, the teleconnections of these two flavors, they are different in magnitude and sign. It has also been discussed in the long run that whether your SST warming now in the Pacific is more EP-like or CP El Nino-like, then that actually influences the blocking projections across the different models. But on the interannual scale, so EP versus CP events kind of influence on blocking. We showed in this paper with Madeleine McKenna, who's a PhD student in the group, that during the, say, DJF peak of the Eastern Pacific events, you have a strong signal there in a decrease in the Pacific, and then you have an increase in Central Europe and kind of this dipole thing there. Only significant changes are shown here. The EP events, though, so they affect the occurrence of blocking, so you have the change collocated kind of with the climatology, whereas in Europe you have this shift. In CP events, it's different. You have a weaker impact, but kind of a shift in the location, and an opposite sign impact in Europe, and kind of similar things you see in JJA. So the point here of this paper was quite a bit that if you use a single index to characterize El Nino like ONI, which is Nino 3.4, then you're missing a lot of this information and a lot of the signal. And we also looked into the duration of blocks during these CP and CP events, and we found that in the Pacific, you can have kind of these long blocking events that are primarily associated with the CP events in gray. In the Euro-Atlantic, these are more the shorter events. And if you find any long events in JJA or DJF, it would be during EP El Nino years. Okay, so you may ask now, as we discussed quite a bit yesterday, how are coupled models doing in simulating the impacts of ENSO on blocking? So at the top here, we have climatology in ERA, and then the Niño-Niña response, or association, I would say. And at the bottom, I have the mean climatological bias in blocking across CMIP6 models, and then Niño and Niño bias. And as you can see, models overestimate kind of this blocking here during El Nino and underestimate Pacific blocking during La Nina, and then they underestimate this Europe/Greenland Ural blocking in both ENSO phases. Now, if you look carefully, you may be tempted to say, well, the biases now kind of seem to follow the climatological bias. So what kind of bias do you have in the response of blocking to ENSO? It could be impacted by the climatological bias, but it could be also that the Niño-Niña bias is contributing to the climatological bias. That was discussed in Dan Seguin and Sun in 2013. They looked at skewness of Nino 3.4 index and whether that could, in the end, when you average everything out and do your climatological bias, actually plays a role. They didn't find a very strong relationship there, but models, CMIP6 models, when it comes to the relative frequency of El Nino and La Nina events, they're actually pretty okay. I didn't, not necessarily for skewness though, because skewness relates to how strong the relative I guess, occurrence of very strong events in both phases. So in any case, I showed before that we believe that, and so flavors play a role. So then it warrants a look at what is the bias for the EP now events and the CP events in the models, and they are very different in kind of location and strength compared to the El Nino events. And the setting is agreement between the models in the bias. So this could be, again, because of how models are doing the EP and CP events, right? So there's a few metrics on this. if you look at the ratio of EP over CP events in models, in coupled models, and then you can separate them in the ones that have kind of a good ratio compared to observations, too strong ratio, so too many EP events, or too weak ratio, too many CP events. And I show here kind of the response to EP minus climatology and CP minus climatology. The contours is ERA 5, and then the shading is what each model group is showing. And I would kind of dare to say that actually the kind of this half of the North Hemisphere is pretty okay when you have a good EP-CP ratio, but it is either poleward shifted, say in the Pacific, or equatorward shifted, depending on whether you have too many EP or too many CP events. But what's going on in Europe, I showed that kind of dipole positive, negative between kind of Central Europe and more of the Ural region, and the opposite in the CP response. That is not getting, we don't see it anywhere apart from maybe the strong, this part here. So that is likely not related to how you're doing ENSO. So you must have some issue with the teleconnection, right? And to look at this, we do have to turn to atmosphere-only experiments. We joined forces with V. Narayanan, and he's running the GFTL AM4 model, and we'll run a set of idealized and traditional Pacific Ocean global atmosphere experiments. So this is GFTL AM4. This is the seasonal just climatology at the top for the historical run. I start in JJA because that's the kind of El Nino year. At the bottom, you have the ERA 5 climatology, and it's pretty good. Then we run a control run that is 50-year simulation forced only by climatological SST. So the frequencies here are kind of similar as what you have in your just AM4 run, and comparing pretty well with ERA 5. And then we run this idealized Eastern POGA and Central POGA experiments, where we impose this idealized evolution of EP and CP events based on composites from the record. They run from June to May. Everything else is climatological SSTs. I only show here the peak. And this is recycled over 50 years. And we also run a traditional POGA experiment where in the same, again, only location in the Pacific, we force with historical SST anomalies and climatologies everywhere else. The reason for this is because we can capture here impacts of the difference in evolution, timing, and strength of the EP and CP events that you cannot get it reflected in the idealized runs. Being that, you can have an EP event peaking in February, or you can have an EP event peaking in November, and that will play a role. So anyways, being a workshop, I'll show some preliminary results. There's a lot to unpack here. Top is response or EP minus climatology. Bottom is CP minus climatology. First column is ERA 5. Then it's the historical run of AM4. Then it's the POGA run. And then it's the idealized EP and CP runs. And, in the Pacific, this kind of dipole here, okay, weaker in the over the Pacific and stronger here. That is okay and is forced by the Pacific. I would say we can kind of agree with that. But I'm still quite puzzled by what's going on in Europe, because in Europe you have this positive, negative. And then if you look at what's forced by just the Pacific anomalies, it is the opposite, it's negative, positive. This is not coming from the Pacific, but in the EP events, it's actually maybe more similar. So there's other things happening, probably the Atlantic, right? But so the historical run captures this positive, negative, but then the Atlantic is not what you see in ERA 5. So this is something that we may be able to figure out with looking at the pacemakers, so now coupled runs, but forced with the Atlantic. So that's kind of the next step here, apart from also doing the life cycle analysis of all these blocks and really understanding how they evolve and why we end up having these frequency differences. All right, so let me summarize so far that I showed you that this relationship between all these different climate modes that operate at different timescales. It does depend on the combination of mode phases, possible two-way interactions. So it really is this kind of wicked problem. I do think that faithful simulation of the patterns of climate variability, it came out in our discussions yesterday as well. It is important. I saw an example with kind of ENSO biases. But apart from how well coupled models are doing with climate variability, without the coupling, we do have teleconnection biases, that is it. And I showed this in this idealized and traditional Pacific Ocean global atmosphere experiments. Now, nevertheless, I think we all agree that it's important to decipher this relationship. Now, the problem being that you have all these multiple timescales is that, and I want to point out it's important to decipher not just because for the sake of it, but also because of whether we can draw potential analogs between climate variability and change, right? So the problem with all of this is that, and that's why I brought the multi-timescale, is that we have a key limitation, which is the length of the record. And for those of us who like paleoclimate, we like to say that now we can, extend the length of the record by looking into past climate. So paleoclimate proxy records have been interpreting as suggesting changes in blocking activity. For example, there is this reconstruction based on tree rings of summer North Atlantic jet, and it has been linked to increases in blocking activity. This is a paper by Chue et al. In 2018. European megadroughts have been, megadroughts of big, long-lasting droughts in the past have been associated with persistent blocks. Lapointe and Bradley showed in the paper a reduction of blocking in the 1400s based on a reconstruction of Atlantic multidecadal variability, and they related that to potential triggering of the Little Ice Age. And Francois had a poster again on Monday on Scandinavian blocking as it is seen in paleoclimate records. So with all these, though, we have a temporal resolution problem. So first of all, it's not, we have blocking activity, but we also have stationary waves and quasi-stationary waves. And our paleoclimate proxies, at best, they are seasonal and most likely, annual and more. So we do need to do some temporal downscaling, really. And one way of doing this is of extracting paleo weather from paleoclimate is to use a machine learning model, or otherwise a fancy regression at multiple levels, if you like. So this is a model, it's a UNet architecture. What it does, it takes as input seasonal surface temperature anomaly, and then it goes through the motions and spits out blocking frequency, seasonal. And this model has been trained on large ensembles, both last millennium and 20th century large ensembles, and era 5, obviously heavily trained on the models because era 5 just doesn't have enough data. So this would be the JJA blocking frequency in these data sets. And in testing, it does okay. This is the kind of mean along the testing period of JJA frequency from this deep learning model, and this is from the test data set. The median pattern correlation along the test data set is about 0.8, which I would say it's okay, good enough for what I'm trying to do here. So now that I have this model, what I can do is use as input a paleoclimate reconstruction of surface temperature that goes back to 750 CE. And the reconstruction I'm using is a 10-member reconstruction of MJJA surface temperature based on these tree rings, this network of tree rings. What you see here is the correlation between the temperature reconstruction and an instrumental data set over the 20th century. And of course, as you expect, you have a better correlation over where, close to where your sites are. But nevertheless, it's one of the better reconstructions of Northern Hemisphere temperature for the last millennium. So, okay, so I can put this in. So this is an example of 1 year of MJJA surface temperature anomaly from this reconstruction. And I can use it to spit out mean blocking frequency, again, JJA. This is the ensemble mean. I have 10 members because there's 10 members in this reconstruction. You can see that, we can capture the what happened to this? Ugh. The blocking, main blocking activity centers pretty well, the Pacific, kind of the Ural, Atlantic situation. The degree of separation of centers depends on the model used for the temperature reconstruction. Oops, this is not working anymore, but follow me
press
here.
the button and drag to the right.
Right, is this,
There you go.
okay, here we go. My other right, okay, hold on, here we go. All right, so nevertheless, now I can look at the variability in blocking frequency along this last millennium. And this is what I have for Euro-Atlantic, Europe, North Pacific, North Hemisphere. So there's a couple of things I want to say here because I need to finish this talk. First of all, we have this reduction in hemispheric decrease in blocking frequency, primarily due to what's happening in Europe and kind of the Atlantic. You see the green here, you may be like alarmed a little bit or a lot. This is observed era 5. I expect this because the input to the model is the reconstruction of temperature. And even if it wasn't, I wouldn't be surprised to see a bias. But what I'm interested in is that I can get the variability, kind of the dips and increases, and that's what I'm looking at here. This little ice age blocking decrease is actually consistent with a tropical Pacific zonal SST gradient decrease. So this is what you see here. This is a different reconstruction of the tropics than what is used, the Northern Hemisphere that's used to create this. And you see this kind of weaker zonal gradient, and then that goes together with less blocking, and that agrees with the Masuera and Endo paper. We do frequency analysis on this. We find increased ENSO-scale variability after the 1600s. And this is also consistent with increased ENSO variance. You see here the running NEO 3-4 variance. This is, again, 2 different reconstructions than the one used here. And there's recent increase in blocking JJA. It is possibly related to this La Nina-like mean tropical Pacific states, stronger SST gradient. So to dig a little bit into this, this is the patterns now, medieval climate anomaly, little ice age, and then little ice age minus medieval climate anomaly. And in little ice age, again, I said there is a weaker zonal gradient in the Pacific. And this is kind of what you see. And we also took all of the periods in the reconstruction that correspond to a weak versus strong gradient. And this is the difference. And so this, again, goes back to the paper by Masuera and Endo that showed that stronger Eastern Pacific warming, that would mean a weaker SST gradient. It is consistent with stronger JJA reduction in blocking in the Euro-Atlantic sector and even a small increase in the Pacific. But anyways, the bottom line of all of this is, again, that we have a very strong two-way interaction between blocking and these modes. It is important to look into how these modes are being calculated in the models, especially going into the next generation. Maybe we need to kind of focus a little bit more on variability than the mean state. There's good reasons for doing either, but that's kind of my pitch. Causality is hard to establish. The analogs between past and future climate change and climate variability can be tricky, and we should be very careful with that. But there's things to learn, and it can help us constrain the relationship with past and future climates. But we do need more data, and a way to get there is extracting paleoweather signals from paleoclimate records. I showed an example of how to do that with deep learning that highlighted the key role of the tropical Pacific, and there is a lot of other ways, maybe, I think, maybe better ways to do this. And with that, I'll leave you with the alphabet soup that was mentioned yesterday. I tried hard to get this because it's hard to get DALI 3 to actually put words there, but PDO I could get. I did it. Anyways, thank you very much.
Thank you so much, Christina, for the wonderful talk. We will save all questions for the end of the session, as we've done before. Next up, we have our next speaker, Pengfei Zhang from the Pennsylvania State University.
Hello, everyone. I'm Pengfei from Penn State University. I'm very happy to be here to share our results. So yesterday there were several talks have discussed the most processes to the west of the blocking. Today, my talk will further discuss its impact to the north in the Arctic. So my topic is from the perspective of atmospheric rivers. and its impact on the Arctic sea ice decline. The first, it's very similar to the studies yesterday. So there are several studies have found that the blocking or anticyclone activities of the Europe can result in the sea ice retreat. So the mechanism can be understood as excessive heat, more moisture carried by the water vapor transport in the warm conveyor belt to the west of the blocking. Those warm conveyor belts can release strong downward long-wave radiation, and the following surface heat fluxes finally results in the sea ice retreat. This concept has been proposed almost 9 or 10 years ago by the. This concept has been proposed almost 10 years ago by the serious work from the Sukuyama's group, and also followed by the Gudrun's work. So they suggest the extreme moisture transport from the North Atlantic can induce the sea ice retreat around the Barents-Kara area. So I read those papers about 7 years ago. So since then, there is a question puzzled me for many years. So it is, to what extent does the melting effect of the moisture transport can explain the rapid decline of Arctic sea ice? So this concept has been followed by many papers in recent several years. However, this question still remains unclear. About 4 years ago, I did a work involved atmospheric rivers. The ARs are long, narrow synoptic jet of water vapor transport, usually observed can be found in the mid-latitude. Actually, it's very rare for AR to reach to the polar regions because of the cold environment in the high latitude. However, in recent several years, there are some more and more ARs has been observed in the polar regions. So since then, I was thinking, so if we can reply the main question I just proposed from the perspective of ARs, because it's a weather event has clear definition, maybe we can partly reply the question from the perspective of statistic method. So, okay. There are a couple of studies that have already discussed the melting effect of ARs in the polar regions. Sorry. Includes the ice sheet melt in Greenland and West Antarctic, the polar events in the Weddell Sea, and the record low Arctic sea ice in the winter of 2016 to 17. So first, we checked the melting effect of ARs on the Arctic sea ice in the past 4 decades. Here we only focus on the November, December, January, which is ice growing season. The variable shown here is sea ice concentration. Normally, the blue color shading denotes the negative values. So it's very clear that the AR exerts strong melting effects on the on sea ice cover, and they are significant. So if we show the negative value in the percentage of its climatological value at each grade, we can see that there are more than half of the sea ice melts when AR making landfall on the ice cover. So, okay, next we just simply check the long-term trend in the AR frequency as shown by the figure on the left. So there is a significant enhancement around the Barents Sea area, and there is a significant decline in the inland area to its south. This increasing trend around the Barents Sea area is robust among three reliances data. To reply the question I proposed in the introduction, here we employed a variable CS area daily tendency, and then we cumulated this value in the 3 months, November, December, January, as shown by the black line here. Actually, this value denotes the seasonal recovery in the early winter. There is a weak positive trend in the black line. So that's because in current climate, the surface temperature in the winter in Arctic is still below the freezing point. So that requires the open water freezing in the early winter. So more sea ice loose in summer, faster sea ice moving in the early winter. So that's the physical meaning of the black line here. Okay, now we can decompose the black line into two parts. One is the CS area tendency during the AR days, as shown by the red line, and another one is that during the no AR days, as shown by the blue line. The red line actually, denotes the melting effect of the ARs. There is a significant trend enhancement in the red line, so that denotes the enhancement of the melting effect of ARs along its frequency increasing. Well, if let's see the blue line. So that means we can, if we exclude the impact of the AR activities, the seasonal ice recovery could even faster. So here we reach one of the main conclusion. So the more frequent ARs actually can prevent the sea ice from going to the extent allowed by the freezing surface temperature. Okay, now based on the red line here, we can further calculate the sea ice area change corresponding to 1% AR frequency change, and then we project this value to the long-term trend of AR frequency. Finally, we compare the results to the total sea ice area decline in past 4 decades and get a statistic results. It is the enhancement of the melting effect of ARs can explain at least 1/3 of the total sea ice decline in winter. So partly replies the main question I proposed earlier. Okay, the last part, we were wondering how to understand the increasing trend of AR activities in the high latitude. So to reach this end, we employed a serious model experiment obtained from the CBCWG group at NCAR. So those experiments are conducted using CESM2. The first one is AGCM run, which is forced by the historical SST time series and the radiative forcing. This is a special pattern of the AR frequency, long-term trend of the AR frequency is comparable to that in the observation. Well, the special pattern is quite different in the fully coupled simulation, large example 2, which is a fully coupled run and only forced by the historical radiative forcing. We compare the AGCM run and the large example simulation. The only difference is the bottom SST conditions. In the AGCM run, the SST time series includes the signals, observed signals of internal variability, such as AMOC, IPO, or IPDO. So we were wondering, if there is a role of the internal variability. So we, well, there are several studies have found that the internal variability from the tropical Pacific can contribute to the polar climate change. So we checked the results in a pacemaker simulation. The pacemaker run is the same as large example simulation forced by the historical forcing and a coupled run, except that the tropical SST normally are nudged to that in the observation. So yeah, it's clear that the results, the spatial pattern of the AR changes is much improved compared to that in the large example simulations. In our climate research community, we usually assume that the impact of external forcing and the internal variabilities are largely linearly additive. So here we can calculate the difference between the pacemaker run and the large sample simulation to get the contribution of the internal variability from the tropical Pacific, as shown by the figure on the bottom left. Yeah, it's clear that the internal variability from tropical Pacific significantly modulated the spatial pattern of AR changes in the high latitude, especially the decline trend in the inland area, and partly contributed to the increasing to the north of Barents Sea. Okay, next let's see the results from the perspective of the magnitude of the AR trend in the region of interest, as shown by the bar chart on the right bottom. The circles show the values in the observation, and the green bar shows that in the AGCM run, we can see that the AGCM can generally capture the observed value. Well, neither external forcing nor internal variability from the tropical Pacific can explain only can explain the observed value. So we conclude that instead, the observed AR trend over the region of interest might be the combined effect of internal variability and external forcing. Okay, yeah, that's all. Thank you very much.
Next up, we have Noureddine Omrani from the University of Bergen.
I will try to convince you that Pacific Oceanic SST front amplified the impact of Atlantic Oceanic front on the North Atlantic blocking. First, I will try to show you what is the primary impact of the SST front associated with the western boundary currents. We know that transient eddies, eddy-driven jet, and the storm track are a very important ingredient for the dynamic of the blocking. And we know that the SST front maintained all these ingredients through the low-level atmospheric baroclinicity or temperature gradient, which is transferred from the ocean into the atmosphere through the turbulent heat flux. I mean here the latent and sensible heat flux. This is, for example, the response taken from our paper, 2019, the response of the SST, of the atmosphere to the SST front. I will describe this experiment in more details afterward. Here is shown the low-level baroclinicity, and you can see that these Atlantic and Pacific SST front maintain the low-level baroclinicity through, here it can be seen here, through the sensible heat flux, through the sensible and latent heat flux from the ocean into the atmosphere. We transferred the SST front into gradient or into baroclinicity in the low level. Oh, sorry. We transferred the SST front into a low level through turbulent heat fluxes. Now, the strengthening of the baroclinicity is associated with the strengthening of the storm track and strengthening of the eddy-driven jet, as shown here. This strengthening of the eddy-driven jet is maintained by baroclinic eddies, as shown here by the A vector. What the atmosphere does, it can be shown here. The atmosphere is dry. This is here the advection of the temperature in response to the SST front, and you can see that the atmosphere tries to offset the baroclinicity induced by the SST front. I didn't show it here, but it is in the paper. This advection is maintained mainly by baroclinic eddies. This is a process that we call baroclinic adjustment. Go into the next. So this is the definition we will use for the blocking. It is just this gradient-based definition with assumption about the region, which should be big enough, and assumption about the persistence, which should be at least 4 days. We will concentrate on this blocking, on Greenland and Euro-Atlantic blocking. This is the experiment now. This is the SST gradient in the shading and the SST in contour. And you can see we have very strong SST gradient along the Gulf Stream and Corusio current. This is the zonally averaged SST gradient along the western boundary current for the Pacific in pink and Atlantic in green. And what we did is we tried just to remove this SST gradient completely. We did that just by assuming that we have the same gradient going from 30° north. And this is how the gradient looked like. You can see that here we don't have this localized SST gradient anymore, as shown here. For the tropical SST asymmetry, we use this, we try to remove the zonal asymmetry, because for dynamical perspective, it is the zonal asymmetry in the tropic which is important. And we remove this asymmetry just by taking the zonally averaged SST. This is the experiment setup we did. We have this zonally uniform SST. It is the first experiment in which we remove everything, SST front over the North Atlantic and North Pacific, and we remove also the zonal asymmetry over the tropic. We have this fall experiment in which we have realistic SST in the tropic and the extratropic. And we have this extratropical all, in which we put only the SST front in extratropic. We have tropical all, in which we put realistic SST in the tropic, but no SST front in the latitude, in the mid-latitude. And we have extratropical Atlantic with SST front only in the Atlantic, and we have extratropical Pacific, in which we have the SST front only in the extratropical Pacific. Now, this is the result. First, here we have this, the climatology of the blocking for our fall experiment for ONCEP in contour. And you can see we can nicely reproduce the structure of the North Atlantic blocking frequency. This is here again, the fall experiment, blocking frequency in the fall experiment in shading, and the blocking frequency in the experiment where we remove everything in contour. And we can see here this primary, maximum of blocking frequency without SST front and tropical SST asymmetry moved from the Euro-Atlantic into Greenland. By putting the SST front, as shown here, that is the response, we move the primary peak of the blocking frequency from Greenland into the Euro-Atlantic, making it more realistic. This is the contribution of the oceanic front only, and this is the contribution of the tropical SST asymmetry, and we can see that both contribute significantly to this response, but the extratropical Atlantic front has a much higher contribution. This is the contribution of the North Atlantic oceanic front and the contribution of Pacific SST front. And you can see that both Atlantic and the Pacific SST front contribute significantly to this shift of the primary blocking frequency from the Greenland into the Euro-Atlantic region. Now, to the dynamic. How that can occur, how these shifts can occur through impact of the SST front. We have three hypotheses. One is through the dynamic of the individual blocking event. The second, through the background response of the background storm creek activity. And the third, through the overall atmospheric circulation. Here, I mean the quasi-stationary eddies. Okay. In order to diagnose the impact of the individual events, we use this tendency equation, which gives us the change of the geopotential height as function of the inverted Laplacian inverted divergent of the vorticity fluxes. And this vorticity flux can be decomposed into contribution of the mean states, contribution of the high frequency eddies, contribution of the low frequency eddies, and the cross term. This is now the dynamic of the individual Euro-Atlantic blocking obtained from the composite using Euro-Atlantic blocking. And then you can see here, that is the 1 day before the reaching the maximum of the blocking, the Euro-Atlantic blocking. And you can see here presented here is in the contour is the anomalies associated with the Euro-Atlantic blocking, and shading is the tendency of the geopotential height. And you can see that these changes in the geopotential height pattern for both tendency and the anomaly resemble strongly to the Scandinavian blocking regime, with west-east wave trend showing pronounced trough in the North Atlantic here, and a ridge over the Euro-Atlantic region. I look it on the contribution, and you can see for both NCEP and fall experiment, this dynamic is very similar. And by looking on the contribution of the high frequency forcing and low frequency forcing, we find that both high frequency and low frequency forcing are contributing. And you can see that the low frequency contribute to the maintenance of this quasi just stationary ridge downstream of the storm track area. Now, this is the composite over the whole life cycle of the blocking, of the Euro-Atlantic blocking for the fall experiment, both front experiment, Atlantic and Pacific. And what this tells us is that both Atlantic and Pacific contribute to the high frequency with higher contribution from the Atlantic. And for the low frequency, we have almost the same contribution from the Atlantic and Pacific. Okay. Now, the dynamic of the individual Greenland blocking events. This is the composite on using the Greenland blocking. And we can see here, this is again the anomalies and the tendency, and we can see the pattern for the anomalies and tendency resemble the negative NAO. And looking on the contribution of the forcing, we can see that both low and high frequency forcing are contributing. And this is now the contribution of different basins to this forcing during the life cycle of the blocking. And you can see that the low contribution to the low frequency is the same, forcing is the same from the Atlantic and the Pacific. And for the high frequency, we have the highest contribution coming from the North Atlantic SST front. Now, now we come to the impact of the SST front on the Greenland blocking through changes in the storm track and the eddy-driven jet. This is how these changes in eddy-driven jet can change the Greenland blocking. It is just the geostrophic balance. When we strengthen the eddy-driven jet, as shown here, we just expect enhancement of the low pressure system over the Greenland. And this low pressure system should be reflected in reduced blocking frequency. And that we can see here that the both front, SST front, act to increase the storm track and the eddy-driven jet through baroclinic eddies. And this increase of the storm track is maintained by both Atlantic and Pacific. This is we don't see here, but the color is means significant. Good. And then you can see here that storm track also is maintained by both SST front. And this means that also the Greenland, the reduction of Greenland blocking is reduced by the impact of the both SST front. Now we come to another effect, is the effect of the reach downstream of the storm track. Also for the Euro-Atlantic blocking, we need not only the moving cyclone, but also the quasi-stationary reach downstream that act to block the downstream migration of the storm track in Europe. This is here, the AD, geopotential height, presented here, and contour obtained from the experiment where we remove everything. And we can see that this reach downstream can exist without the SST front and without the tropical SST asymmetry. But what the SST front is doing, it increase and strengthen this reach through both impact of the Atlantic and the Pacific SST front. And we can see that the biggest contribution is coming from the Pacific SST front through this wave train that's propagate from the Pacific into the Atlantic, as shown here by plane vector. So we come now to the conclusion. The SST front and tropical SST asymmetry improve the wintertime North Atlantic blocking frequency with the joint impact of the Atlantic and Pacific playing a crucial role. The Pacific SST reinforces the North Atlantic blocking Atlantic circulation storm track, AD-driven jet and reach in Europe, which favor the shift of primary blocking center from, I changed it, Greenland into Euro-Atlantic region, making the blocking frequency realistic. The enhanced interaction between storm track and the European reach in response to the joint impact of the Atlantic and Pacific SST front favors the occurrence of the Euro-Atlantic blocking, and the strengthening of the Atlantic AD-driven jet and the storm track in response to the joint impact of the Atlantic and Pacific SST front reduces the Greenland blocking frequency. And this just through this geostrophic balance. When we increase the AD-driven jet, we should decrease the geopotential high or pressure, and therefore we should decrease also the blocking frequency. Thank you.
All right, thank you, Noureddine, for the wonderful talk. Our last speaker in this session will be Andrea Vito Vacca from Politecnico di Torino.
Like that? Oh, yes. Good morning, everyone. I'm a PhD student from the Polytechnic University of Turin, northwestern Italy. And today I'm going to talk about how the projected weakening of the Atlantic meridional overturning circulation shapes the evolution of the large-scale Euro-Atlantic atmospheric circulation. First of all, I want to acknowledge the co-authors of this work, especially Katinka Bellomo, my supervisor, which is in the room, for her great support since the first day. Under climate change, the evolution of large-scale atmospheric circulation in the Euro-Atlantic sector is uncertain. The large intermodal spread in future projection has been attributed to the uncertainty in the future evolution of the meridional temperature gradient, which is a key parameter controlling the baroclinicity of the atmosphere, as well as the variability and the speed of the jet. The spotlight is on the tug of war between two climate change processes, the Arctic amplification, which acts to reduce the low-level meridional temperature gradients and theoretically promotes a weaker and wavier jet stream that is shifted to the south, and the upper tropospheric warming, which increases the high-level meridional temperature gradient and theoretically promotes a jet stream that is shifted poleward. A third component is the cooling of the lower troposphere in the Arctic latitudes, which acts to even more increase the high-level meridional temperature gradient. The interaction between these climate change components has been attributed as being connected to the squeeze in the narrowing of the North Atlantic jet in the winter and the intensification of the storm track, which are the signals emerging from the state-of-art future projections. In this context, less attention has been given to the role of the ocean. In particular, the Atlantic branch of the thermoline global circulation, the EMOC, transports a huge amount of heat from the equator into the North Atlantic. And while previous research already stressed on the importance of the HEMOC for the mid-latitude circulation, the impact of the HEMOC in future projections on the uncertainty of the circulation is still largely unknown. In particular, the HEMOC is predicted to weaken under greenhouse gas forcing, despite a very large intermodal spread, as you see here in this plot, showing the HEMOC strength anomaly under the SSP 8.5 forcing that weakens steadily during the 21st century. So we investigate that, the impact on the large-scale atmospheric circulation, analyzing 3 experiments from the CMIP6 archive, the SSP 4.5, the SSP 8.5, and the abrupt 4x O2 simulations, in order to highlight the influence of the HEMOC into the large-scale circulation. We split the 3 ensembles in 2 groups based on the projected HEMOC weakening at the end of the simulations, so that each simulation is classified either as a large HEMOC decline model or a small HEMOC decline model. And then we interpret the difference between the atmospheric circulation responses between the 2 groups as the effect of the different HEMOC weakening. We started by analyzing changes in the climatological surface temperature in winter under the SSP 8.5 forcing. In the upper left of the slide, you see the response of the large HEMOC decline model, the ensemble mean response, that is normalized by the degree of global warming in order to account for the different climate model sensitivities. So you see the reduced warming in the subpolar North Atlantic, known also as the North Atlantic warming hole, which is more pronounced in these models than in smaller HEMOC decline models. We also plot the response of the mixed layer depth, which is indicating a reduction of the HEMOC deep convection. If we then explicitly compute the difference between ensemble mean responses of the 2 groups, and we overlap with the white contours the difference in the response of the mixed layer depth, it is clear that the difference in the temperature patterns are actually driven by differences in the ocean circulation responses. And this means that we are actually isolating the signal of the HEMOC decline. Overall, we observed that in large HEMOC decline models, there is a cooling, a reduced warming of the North Atlantic, in particular in the North Atlantic warming hole area, then propagates up into the atmosphere. On the left, the difference in the responses of the zonal mean air temperature that shows the relative cooling of the atmospheric column in models with a larger HEMOC decline, especially in the high latitudes, meaning that models with a larger HEMOC decline also show reduced Arctic amplification. Then impacts on the meridional temperature gradient that is plotted on the right. So models with a larger HEMOC decline show an increasing meridional temperature gradient compared to models with a small HEMOC decline. And this impacts on the mean circulation response. So we plot here the zonal wind change at 250 hectopascal, the difference between the large and small HEMOC decline models that highlights the intensification and elongation of the upper level jet stream towards Europe. And with the same procedure, we compute the response of the storm track, which is an intensified storm track in its downstream flank, especially in between the British Isles and Ireland, in the center of action of the NAO. This is consistent with the increased baroclinicity of the low-level atmosphere induced by the reduced heat transport from the ocean circulation. In addition to changes in the mean state, we also computed changes in the daily variability expressed by the Euro-Atlantic weather regimes, which are shown here. The shadings are the geopotential height anomalies composites of as classified by the K-means clustering, while the black contours represent the composites of the eddy-driven jet, the low-level westerly flow. So out of the 4 weather regimes, 1 is unblocked, the positive phase of the NAO. that show a central position of the eddy-driven jet. And the other three are blocked regimes. So the Scandinavian blocking, characterized by a tilt eddy-driven jet position from southwest to northeast, the Atlantic ridge, characterized by a poleward shifted jet, and the negative phase of the NAO, characterized by the Greenland blocking that push the eddy-driven jet south. We found a very significant sensitivity of the NAO plus frequency of occurrence to the AMOC decline. In particular here, we show multimodal NAO plus frequency anomalies. The purple boxes represent the three experiments, the SSP 4.5, the SSP 5.5, and the abrupt 4x CO2 simulations, while the black stars represent the significant increase of the NAO plus frequency compared to the control simulation, the historical and the pre-industrial control. So that under the greenhouse gas forcing, the models respond with an increase in the NAO plus frequency. If we then split the multimodal distributions into the two groups, the large and small AMOC decline group, the reddish and the bluish boxes here, we observe that models with a larger AMOC decline also predict a larger increase in NAO plus frequency, so that the multimodal NAO plus frequency increase is actually driven by models with larger AMOC decline. We show that also with the time series of annual frequencies of NAO plus in the three experiments that highlights how in the simulations the NAO plus frequency increases more in models with the larger AMOC decline. And we also computed a multimodal linear regression with the three experiments between the projected AMOC weakening and the NAO plus frequency change that results in an average increase of 0.9% for each Svertrup slowdown of the AMOC. Analyzing only CMIP6 experiment is actually impossible to disentangle in an ambiguous way the effect of the AMOC weakening to other processes and feedbacks that happens with the increase of greenhouse gas forcing. Therefore, we also analyzed an ad hoc experiment performed with the ECR3 climate model, the details of which are going to be detailed in a paper that is currently under review. But basically, we compare an abrupt 4x CO2 experiment in which the AMOC is weakened, the red line here, with another experiment in which in addition to the greenhouse gas forcing, a positive virtual salinity flux is applied in the northern North Atlantic so that the AMOC is fixed at its pre-industrial level. And in this way, we are able to disentangle the effect of the AMOC from all other processes that happens with the climate change. We found very consistent results in the mean circulation. So an increased low-level meridional temperature gradient in the weakened AMOC experiments compared to the fixed AMOC experiment, and also an intensification of the upper level jet, and that is elongated towards Europe with this tripole pattern, and also the intensification of the storm track in its downstream flank. Also, the weather regimes analysis were consistent. So ECR was actually one of the few models in which if with the greenhouse gas forcing, the NO plus frequency decreases compared to the mean ensemble behavior of that show the opposite direction. Nonetheless, if we fix the AMOC to the pre-industrial level, the NO plus frequency decreases even more, so that the difference between the two is actually an increase in the NO plus frequency with the weakened AMOC. Why that? Why does the AMOC decline increases with the NO plus increases the NO plus frequencies? Our interpretation was that the climatological forcing of the AMOC on the subpolar North Atlantic, on the temperature, propagates up into the atmosphere and affects the mean geopotential height, which respond with a negative anomaly on the center of action of the NAO. And this, from a weather regime perspective, from the daily variability point of view, projects onto an increased number of days classified as NAO plus with the algorithm. So in conclusion, the weakening AMOC leads to a wintertime zonalization of the jet, an enhanced storm track in its northeastern flank, and more frequent occurrence of NAO plus days, with possible consequences for the storminess and extreme events, especially in the Western Europe. The AMOC decline is a key driver for the evolution of the Euro-Atlantic atmospheric circulation. And therefore, if you want to reduce the future uncertainty in the large-scale circulation, we need to better constrain the ocean circulation and its evolution under climate change. Thank you.
All right, thank you so much to all of our speakers for all of the wonderful talks. At this time, we're going to switch to our open discussion and allow people to ask some questions. So if all of our speakers could please come up and have a seat in our table up here, and we can get that started. As a reminder to those of you who are virtual, please raise your hand if you have a question.
I have two questions. First for Christina. So you talk about using deep learning to learn blocking frequency, and you train your model based on the present climate, and then you extrapolate to the past climate. Have you tested the extrapolation based on some model simulation at all? Because very often machine learning is good with fitting the data, but they don't always do very well with extrapolation.
So I checked because the purpose was the little ice, I think that's the question, the little ice age versus medieval climate anomaly. I actually looked at the last millennium ensemble, and the difference is there. It depends, it's 10 ensemble members, and there is the decrease in blocking, that same pattern that I showed that comes from the reconstruction in about half of the ensemble members. But when you put all of them together, the ensemble mean doesn't show significant difference, but each ensemble member separately, kind of the direction is that in the LME, which is the run with the orbital and volcanic forcing and sun forcing. So it is consistent, but we know that the models have struggles with simulating the extent of the changes that we infer from the proxies for the little ice age and the medieval climate anomaly. And that's why, you know, using the machine learning or any kind of reconstruction rather than a free run can give us different results.
Yeah, I agree. This would be a great method. It's just when you play with neural network with extrapolation and you want to know whether this is doing well or it just based on some non-linear extrapolation.
And the other thing is that in the training of the model, we used both the large ensemble 20th century and the large millennium ensemble in order for the model to have seen, you know, conditions like those that are simulated by the models in the large millennium. So it does have that information. So it's not exactly extrapolation altogether.
Great, thanks for the clarification. So I have another question, perhaps for all the speakers. So yesterday we talked about different processes for blocking, and that was wonderful. But when we moved on to climate variability, very often we just show statistics. So I wonder, what do you think about what we could do to incorporate those processes into analysis on the longer time scale? I think Noureddine showed some volatility analysis, but that obviously doesn't include all the things we talk about, which we thought would be important. So have you have any thoughts or recommendation? My question is, when you look at the longer time scale, and most of the time we just show statistics of blocking frequency changing, including my own work. I'm just wondering, like, what can we do to include the process we talked about yesterday, like change up the upstream conveyor belt or heating, or I don't know what else we should include, but I think it would be good to help the community to decide, should we just continue to go with analysis of blocking frequency, or should we consider some simple process to incorporate when we analyze the longer time scale?
Okay, I have to hold it. For the low frequency, I think the most important, what makes the low frequency variability is the blocking frequency. I mean, we get the low frequency just by moving the distribution from one state to the other, and the probability of getting, if we look in the perspective of large-scale circulation associated that maintains such blocking, for example, NRO, or other pattern, as of we're looking in my analyzing the low frequency variability, it was like that. When we have IMV positive, we have higher frequency of the occurrence of negative NRO. This is what we see as a low frequency. It just you get higher probability to get negative NRO in one phase than positive NRO. I mean, for multi-decadal variability or low frequency variability, I think the frequency is very important. And yeah.
I think one of what you're getting at is sort of what in the runs that we're running, the idealized, we need to look into the life cycle analysis. And there's, instead of doing okay, let's take EP, CP, or NAO positive or negative and doing the frequency composites, you can go the other way, look at the blocks themselves, the type of block, look at the processes, how they're different, and then do composites or look at the conditions associated with the different types of blocks. So kind of go the other way and start from the weather to go to climate instead of start from climate to go to weather, which is what we typically do. And I think and that's why I really love this workshop, because now there's so many ideas about what needs to be done in order to merge the approaches and or at least bridge them, not merge them, but bridge them, because it's important. And as we discussed in the breakout sessions, I think that there's no way to improve things if we don't look at the building blocks of things. Building blocks. Okay, that was another pun intended.
Go ahead.
Thanks. First of all, thanks for the nice talks. Teleconnections are really important, especially if we're talking about how well we're trying to represent in models. I just have a question for Christina. You found the association between tropical Pacific and North American blocking. I was just wondering whether, have you tested with the same association with PNA pattern and North American blocking? If not, do you feel it should be more stronger association than related to tropical Pacific assist?
Wait, let me understand. If I looked at the PNA pattern, just the PNA pattern.
Associated with Northern American blockings?
Okay, no, I haven't looked at that. So kind of build the pathway, you're saying, between the frequency and actually the, I haven't looked at that, but that's.
Feel there could be stronger association compared to tropical Pacific. That's what I'm very interested in.
Oh, okay, you're saying that the PNA and blocking, not to go from the Pacific to PNA to blocking.
No.
Okay.
Yeah.
Right. I mean, PNA, though, is partly forced by the tropical Pacific,
Yeah.
right? And I mean, these experiments, I don't know if you're referring to the experiments, the ones with the idealized and the POGA runs. I mean, those are, whatever we see supposedly is forced by the variability in the tropical Pacific only. So, but I think it's a good idea to look at, the pathway probably. So, and associate the PNA with the forcing, being that this is the target of the experiment.
Yeah, because I haven't read any study about PNA patterns and biases over Pacific blocking regime. And I think it's kind of important because two sides that we refer to, one is from Alaska and one is West Russian side. And we usually get different features if we compare the bias in models. So that's why I was just interested have you tested that, or it could be a really interesting idea. So yeah, thanks.
Yes, thank you for that.
Hi, I have a question for Andrea. It was interesting to see that your results is largely consistent with, I think, Ray Chimke's work using single model. And I wondered, what drives the spread of the AMOC in the models, and is it consistent with the method you use to do the fixed AMOC simulation?
Well, this is a great question. I mean, there is not an established answer on this. There is great spread on the model projections of the AMOC. The interesting part is that there is also a large spread in the mean state of the AMOC. Therefore, we are trying, the next step of our analysis was also to analyzing what happens in the mean state in the historical simulations, how this is going to project onto the future. So there is already disagreement between models in the mean state, and that's why we need to better constrain ocean circulation in general, and then also this would help to constrain the future of the ocean and also on the large-scale circulation.
Hi, Rainer Schumann. That's a question for Christina in the first instance, I think. When you nicely reviewed all these results we have for teleconnections of the alphabet soup with blocking, I got the sense that most of our results are for Northern Hemisphere winter. Is that fair to say? And is there leverage of maybe paying more attention to summer, or is it just more difficult?
I think, yes, most of the results are referring to winter, not the summer. There was, which ones did I can't remember off the top of my head, but indeed, most of the papers that I think I reviewed refer to winter. So going back to that discussion we're having about the different relative importance of processes in the winter and summer, I think that plays a role. And also even in our idealized runs, I mean, I focused and I showed winter because the summer is such a mess. But in the paleo kind of blocking thing, now the most of the proxies actually refer to the summer season because it's tree ring growth and it's more summertime. So I feel that maybe like there's a slight chance that we can get some information from that about the summer or kind of constrain something, because yeah, indeed, it's very difficult. Summer is just, and the shoulder season's even worse. Yeah.
Okay, thanks.
I have a question for Christina. Excellent talk, very informative. In one of your slides, you cited a previous study that shows the connection between blocking and the negative phase of PNA. Basically, like blocking helps to maintain the negative phase of PNA. A similar link also exists between blocking and the negative phase of NAO. This kind of reminds me of Olivia's talk on the first day about recurrent persistence. So I was wondering if like, does this imply like blocking would, like one blocking event would precondition the environment for subsequent events, but such kind of preconditioning would only happen, say, under certain phase of the climate mode. Does that make sense? I don't know if anyone has done something like this.
I don't know, but I think it's a great idea, because then and it kind of goes back to some discussions we had over the workshop that, right, the recurrence versus the persistence, probably we can find recursors or, you know, required conditions that are forced by the different modes that actually kind of allow for the recurrence to happen more often, and then that's what shows up in the statistics compared to persistence. So separating the two is probably, I don't know if there's literature on that with respect to climate variability, but I think it's a great idea to look at that.
Hi, I just want to thank speakers. Great talks. It's really interesting stuff. I had kind of two quick comments. One was your comment was really good. And in particular, I'd point out that the spring for the subseasonal folks is a big problem, right? Because you kind of have a continuous jet to a split jet. And when that happens, causes a lot of problems for predictability. And incidentally, it's a function of Melissa Breeden, who's a couple of folks behind me, has a real nice paper on, things like ENSO and things like that project onto that, and it just causes a lot of problems. So for those young people who are looking to answer Lance's and Carrie Emanuel's calling for subseasonal to seasonal, Christina's talk is a great outline for a lot of the problems that we're trying to deal with that. I do have one comment. It's more an interpretation comment about the PDO. As you mentioned that, there's finding the connection between ENSO and blocking and the PDO and blocking and how you get differences. I suggest that the interpretation of those things you need to be a little careful in the following sense. So I kind of think of things like ENSO, the MJO, sudden warming, QBO as kind of, you could argue they're sort of intrinsic actual dynamical modes of the climate system versus things like the NAO, which have, their statistical artifacts of, I don't know, for lack of a better word, daily weather ability projects on them, ENSO projects onto them, SSWs project onto them. And so it's really a multi-time scale object, right? It's not like an intrinsic thing. And I would say that the PDO is really the same thing. I can put you to, this is not my area of expertise, but there's a real nice review paper on this that kind of bridged the oceanographic and atmospheric communities. And what they showed is that you can really break the PDO down into, there's 3 eigenmodes of the system, and one is a North Pacific piece, but really, arguably the 2 important pieces are eigenmodes that represent the flavors of ENSO. And when you add those all up, you recover the PDO. So the PDO itself is another one of those things that's not like a, does that make sense what I'm saying? So when you say that it's ENSO is not related to, but PDO is, it's kind of, you just have to be a little careful with how you're.
No, I don't. I absolutely wouldn't say that ENSO is not related to PDO because, and we have work on this where you have multi-decadal variability of ENSO regimes that in the end could be tied to the zonal gradient, and which one expression of that is the PDO, right? So yeah, no, absolutely. That's why I said in my first. So I'm not separating them. I just going over the review of what people have done and how they, right? I mean, there's value in that as well. But right, yeah. But as I said in my first slide, the fact that we have this multi-scale variability in all of it, and so intrinsic variability of ENSO and also of ENSO predictability without forcing, it is there, yeah. And you can torture the numbers and get PDO or any other index you want in some sense, right? So I think absolutely that's what makes causality very, very difficult in all of this. And then you put blocking in the mix and then it's even worse. I'm not saying that doesn't mean we should give up. And I think that there's.
Yeah, we need that. Like those are the things that are going to imbue the system with predictability, and then blocking is the high impact thing that causes us that people want to know about.
And it's the thing with indices, right? Like they can be useful, for example, in the forecasting community or kind of understanding that it doesn't mean that they necessarily represent the processes in the different timescales. But right now, today, if what each index, what sign it is, it matters, right?
Yeah.
So that's, again, kind of breeds of weather and climate and how we think about things.
Great. Thank you. It was good talk.
Thank you. Thank you.
A question for Andrea, and thank you for the great talk, because I think the framework of using weather regimes to look at future climate change, I think really encapsulates some of the goals of this workshop of really bridging weather and climate. So I think that's a really nice kind of manifestation of that. My question was that given the results seem to depend so much on the sort of thermal impact of the AMOC on the vertical structure of the atmosphere and therefore the vertical structure of the variability, whether you'd looked at surface pressure, sea level pressure, given that, for example, cooling, you could imagine that inducing an anticyclonic tendency, and then how that might manifest in terms of the traditional sea level pressure based NAO index as opposed to the Z500 regimes.
We didn't, but that's a great suggestion. So thank you. I think
we can talk a bit more about it later.
We can talk about it later. Thank you.
Hey, Dr. Omrani. I just have like one quick thing I want to confirm. So when you do those experiments, the topography is kind of like real world experiment. That's very cool.
Topography is, I mean, the idea of this experiment is, we call it some semi-idealized experiment. We take from the real world something way to see what's impact of this process on climate when we drive the model with climatological SST. And there is two ideas behind that. We know that in the tropic, it is the zonal asymmetry, which played a crucial role for the dynamic through this Bjerknes feedback. And in the extratropic, we know that it is the meridional SST front, which play a crucial role for the maintenance of the AD dynamics. On this is we just start to play around with, try to play around with these processes to see, to interpret the climate when we drive it with climatological SST. But everything is real world.
Yeah, thank you. I have a question for Christina. You know how much I like paleoclimate. I audit your paleoclimate model classes. I'm wondering, so it's really great to hear that we are able to like downscale on a time scale to see like a weather, kind of like weather time period for the paleoclimate. I guess my question is like, when can we use that to predict something, say blockings or like what type of weather we're going to see more? Because not like all heat waves are related to blockings.
I mean, I think the way that we've been using paleoclimate is, first of all, with respect to analogs or reverse analogs to the future from the climate perspective, and also, I guess, to inform and constrain kind of these relationships. And you can build hybrid models from that, or you can get help from paleoclimate into kind of, and paleo weather if we're able to extract that for now for forecast. If you're asking for forecasting specifically, I think, I mean, I guess I don't know. That's a good question. We can find some creative ways. One thing I wanted to say, though, I wanted to point that out, is what I did in the results that I showed is that, okay, I did this temporal downscaling from seasonal surface temperature to a seasonal blocking, right? And that applies to, you know, the tree ring kind of data that I had. But I think that it's important to point out for those that are not necessarily familiar with paleoclimate proxies, that there are proxies like what Francois showed in his poster, and then also tropical proxies that we use for El Nino that actually record the extreme events. So they record the events at those daily scales, even though the resolution of the proxy itself, you know, is longer. But the signal in the proxy is not necessarily an average seasonal signal. It's extreme, an extreme event that happened over 2 or 3 days. So I think that that's also important to consider. It wasn't necessarily, it didn't come out from what I was doing because it was a little bit different, but I think that's important to know.
I think in Pacific Northwest, we have lots of caves and trees. Possibly we can get reconstructions from them.
Yeah, there are a lot of, and all of these paleo data simulations, they're using networks of data that include everything, and they're very sophisticated.
We have a virtual question from Bao. Feel free to ask your question.
Yeah, thank you all for this very nice presentations. Yeah, this is Bao Xiang from JFDL and also UCAR. So I have one question for Noureddine, another for Christina. So the first one is that you show this front in the North Pacific and also North Atlantic. If we include this front effect, the blocking will be reduced in the North Pacific, but increased in the North Atlantic. So many of our models suffer this bias with overestimate North-Pacific blocking but less underestimate North-Atlantic blocking. So I'm just thinking about whether that is related to the model resolution. If we increase the model resolution for both atmosphere and the ocean, do you expect that we improve this blocking simulations?
Push the button.
Have paper in 2022 or 23 together with Panos, who was the lead author, where we try to compare the high and low resolution model. The paper was introduced by, and in general, we do improve the bias, but there is not ideal. There is still bias, but we do improve bias by increasing the SSD front. And the big problem in the models, especially in the Atlantic, that this transition from the Gulf Stream into North Atlantic current is really zonal. This means you don't have very strong quasi-meridional component that transport the heat northward. And from that, we get a sort of cold bias. And this cold bias, through this, what I presented, will be associated with changes in the SSD gradient and changes in the baroclinicity, and therefore also changes in storm track blocking and the eddy-driven jet. And this is what has been shown in this paper. And by improving this SSD bias, we do get improvement in all these ingredients, like shown with the same mechanism shown in this work.
Okay, yeah, thank you very much. So another question that Christina showed that based on this paleoclimate reconstructed blocking. So in the last century, or even from 1950, there's an increase in blocking frequency in the Northern Hemisphere for both Atlantic and North Pacific. So yeah, yesterday there's also a presentation showing that for the CMIP future projections, blocking frequency is projected to be there's a decreasing for the CMIP model. I'm just thinking about how to reconcile these two results. Is that due to a multi-decade variability in the observations, or is there something else?
I think,
Thank you.
thank you for the question. I think that so the paleoclimate reconstruction we're showing was JJA, right? And I think if you look at, say, Wooling's 2018, for JJA, there is some increasing trend that is significant across the methods. And in this work that I showed, I think I tried to make sense of it, relating it to the La Nina-like pattern in the last maybe 3-4 decades in the tropical Pacific that is consistent with that increase. Whereas, if you go into the future and the projections, I think a lot of the decrease is associated with the fact that the models are producing, as far as the Pacific goes, right? I'm not, okay, surface temperature gradients and upper and lower level, that is a part of the story. But as far as the Pacific is concerned, the models are projecting rightly or correctly or wrongly, I don't know, a El Nino-like pattern in the tropical Pacific, which is the opposite from the last few years. So then if you have a decrease in blocking in the future projections, that is consistent with the decrease in the zonal gradient or the El Nino-like change. But in the past 30 years, we've had the La Nina-like state in the tropical Pacific. So I think that these are consistent as far as the tropical Pacific goes. I will, put an asterisk there for the zonal temperature gradient, meridional temperature gradients. But it is shown in observations, the JJA, not DJF or anything else, but JJA specifically for an increase.
Just a quick follow-up. So have you looked at the DJF from your payload climate? Do you have that results as well?
No, because I focused on JJA because the proxies, even though there are paleo data simulation products that include DJF, these three-ring proxies and this specific reconstruction that is one of the better ones, it is on MJJA exactly because this is the growth season for the rings in the for the trees in the northern hemisphere. So I feel it's a little bit better constrained to look at the JJA.
Okay, thank you very much.
All right, let's go Melissa first, and then we'll move on.
I have a question for Noureddine. So I'm trying to kind of piece together the idea you put together at the beginning where it's like the local SST gradient amplifying the eddy-driven jet, which makes sense. But then how does the Pacific front impact blocking over the Euro-Atlantic more than having the Atlantic front, right? Like, is there a possible other teleconnection, like maybe through the stratosphere or something that's also happening from the Pacific to the Atlantic?
Press the button, please.
This case, I don't think stratosphere. I analyze stratosphere. There will be paper on that on stratosphere. There is two way. There is this downstream impact of the strengthening of the eddy-driven jet over the Pacific. If you look on that, you have really this downstream impact. The strengthening of the Pacific jet is not limited to the Pacific. It goes through the whole North America and into the things here. We found also this quasi-stationary reach. And this is maintained through this wave trend that's through plumb vector, that's shown through plumb vector that goes from the Pacific into the Atlantic. We know this wave trend from ENSO, from lots of other teleconnection pattern. And the thing, the response we get in Pacific, I didn't show it, it is really a big strengthening of the allusion law. And this is very, very similar to what we see in case of ENSO one phase. And we know this can, I think you're right, this we know that can impact the Europe through tropospheric bridge, through this wave trend, but also through the stratospheric bridge. But we have very strong stratospheric trends, but this stratospheric trend doesn't propagate. We have awakening of the vortex through the stratospheric, through this wave, through this strengthening of the allusion law. But this change, this stratospheric change doesn't propagate to the troposphere because we have very strong jet in the troposphere maintained by the tropospheric it doesn't really propagate into the troposphere. This is that make me conclude that it is mostly this tropospheric bridge which maintained these changes in the Atlantic.
Thanks. We are out of time, so we'll do just one more question. So sorry, go ahead.
Hi, I have a question for Andrea. So I was just a little bit confused in your conclusion slide. So you were saying that you get more zonalization of the jet and more positive NAO due to the AMOC weakening, but the positive NAO has a more tilted jet, right, compared to the negative NAO, which is more zonal. So I was a little bit confused, and I guess I was wondering if you can also repeat the main argument about how the Atlantic Hall, I mean, I guess it creates an intensification of the gradient equatorward of it, which maybe you can expect a more zonal jet, but then it doesn't agree with the NAO change. So I was just wondering if you can comment on that.
Well, okay, yeah. In my knowledge, there is more zone, even from what we've of the on the eddy-driven jet with the is classified as NAO plus. There is more shifted north, the eddy-driven jet with NAO plus, compared to the NAO negative, which is shift south. In our methodology, from how we computed the weather regimes, the NAO plus is connected with a central position. But if you compute, I think, the weather regimes in a different way, maybe you decide on a different number of clusters, and you have maybe the NAO plus together with a blocking that maybe tilts the jet, then maybe you have a tilt jet connected to that regime. In our methodology, the NAO plus was associated with a central and zonalized eddy-driven jet.
Maybe we can compare results in break.
All right, so just as a quick reminder before we thank our speakers, we're going to go to a break next, and then we're going to come back at 10:45 for our last session, which is on climate projections and impacts. So let's give a round of applause to our speakers. Thank you so much.
Okay, welcome back, everyone. We have our final session now. This session is about blocking. And in particular, blocking and climate change, which we've been kind of building up to all this time. So very pleased to have Pedram here to give our invited talk. So Pedram has half an hour, and as normal, we'll do the questions at the end. So welcome, Pedram.
Okay, great. Well, first of all, I'd like to thank the organizers for putting together this great workshop and also for the invitation. So most of the work that I'm going to discuss today is from Ibrahim's PhD thesis. He was my student at Rice and is now doing machine learning for extreme weather events at Versic. And also Sandro, who was a postdoc in our group, has contributed a lot to some parts of this work, as you'll see. Okay, so we have talked a lot about blocking events and their role in driving some types of extreme events, particularly heat waves. But also here, I wanted to point out their potential role in also just exacerbating other types of extreme events. And I think one example of this is the interaction of blocking events with hurricanes. For example, Hurricane Harvey, which is you see it here, famously stalled over Houston for 5 days, and that's why we got so much rain and record-breaking flooding. And as we have shown, and a number of other papers have shown, this was because there was a blocking event that formed here. It basically pushed the hurricane down, and that's why it stalled. So I wanted to highlight this example to point out that there are other properties of extreme events, like of blocking events, like their size, that also we should care about, because that would determine basically how far the influence might go. So there are key characteristics of the blocking events that we like to understand how they might change with climate change. Of course, there's frequency, but also there's size, duration, intensity, the 3D structure. Basically, broadly, I mean the vertical wind, the thermal structure inside the block and its pattern, and also the location of the blocking events. And I think this is also, as already mentioned earlier, this is also something very important. Even if climate change wouldn't change the duration or intensity of the blocking events, just changing where these blocking events happen, that can have a big impact, because places that when the people and the infrastructure are not ready for a specific type of extreme event, I think that this actually might be a more important characteristic to look at. For example, I lived in Houston for a few years, and every time that the temperature drops to like 31 degrees Fahrenheit, like the whole city shuts down for a week, because people are not used to dealing with cold weather. But then it can get pretty hot in the summer, and the infrastructure is pretty resilient. On the other hand, the kind of winter that we had in Houston and resulting in like $200 billion of damage would be a regular winter day in Moscow. But then the kind of heat wave that was so destructive in Moscow would be just a regular summer day in Houston. So I think these kind of changes in the location of extreme events can be very important. And of course, as already been mentioned, also understanding how changes in these characteristics of the blocking events might change the characteristics of the heat waves or other kind of extreme events. This is also something very important. It may not be that straightforward, and I'll mention a couple of examples. So many studies have looked at the change in the frequency of the blocking events. As as you know. Team has a very nice review paper from 2018 that summarized the state of the art until then, and I don't think it has changed much since then. For example, this is a figure from that paper looking at winter and summer, 3 different blocking indices. The shading here shows the change in the percentage of days in each season that blocking event occurred until RCP 8.5. And sort of, if you kind of zoom out, it's blue, so there's a decrease in the frequency. But also, if you look more carefully, for example, with the anomaly-based index, there are areas when the blocking frequency would increase, but then you don't see that in the reversal index or in the hybrid index. Also, you see that there are a lot of dots here, and those mean that the model didn't agree on the sign of the change. Also, there's another figure in this paper that showed the bias compared to era 5, and you see that the bias is actually as big as the signal. So probably there is a decrease in the frequency, but also there are a lot of uncertainties and dependency on the index and the GCMs. But then the next question is, if the frequency of the blocking event decreases, what would that mean for the frequency of the heat waves? So when I was a postdoc with Ziming Chen at Harvard, I started working with one of his PhD students, Packard, and we started looking at this kind of relationship between the heat wave frequency and the blocking frequency to evaluate the blocking indices. We published a GRL paper on that, but later in his postdoc with Matt Collins at Exeter, Packard started looking at how this relationship might change with climate change. So here in this plot from his paper, every data point is basically the average over a season in a given year. And you sort of see that there's a yellow line here, which is hard to see. The blue line is from the future climate, so you kind of see that this slope actually changes with climate change. And in this paper, they found that that's actually more important than the change in the frequency of the block itself. For example, this is a sentence from that paper. So over Europe, when the historical heat wave frequency is around 2.5%, just a decrease in the blocking frequency would reduce this number by 0.6%. But then the change in the slope of the heat wave blocking frequency relationship would actually increase this number by 1.4%. And this is with this warming, the average warming taken out. So just the effect of the blocking on the frequency of the heat waves doesn't have a direct relationship with just the frequency of the block themselves. And this is also something that others have looked at. For example, again, from Tim's paper, there is a sentence about this blocking and extreme event relationship, and it's followed by a number of examples. But also I wanted to point out that in this paper, Packard looked at just a simple relationship between just the frequency of the blocks and the frequency of the heat waves. But of course, we can imagine that just the change in the size and the intensity and other properties of the blocks and the heat waves probably could even be more important if we care about the impact. So in Ibrahim's thesis, we started thinking about how the size and the duration of the blocking events might change with climate change. And here by size, I basically mean the area, the spatial extent of the blocking events. And our thinking was that if the blocking events become larger, they are going to be more impactful. They are going to lead to larger heat waves affecting more people. Also, you can imagine that this can increase the mixing lengths and affect the horizontal thermal advection. We didn't confirm any of these basically relationships, but we assume that that is a reason to also think about the size of these blocking events. And the results that I'm going to show, they were published in this GRL paper in collaboration with Da Yang, who is now my colleague at University of Chicago, and Libby Barnes. So we started by looking at 2 large ensemble simulations from NCAR and GFDL, and we look at changes under RCP 8.5. We used a simple anomaly-based index with a 7-day threshold, and we used 7 rather than 5 because later we applied this to the QG system, and in QG 5 days is just too short for blocking events. And to calculate blocking area, we basically find these 1 standard deviation contour lines and calculate the area inside. But the results are not sensitive really to these exact definitions. So here are the results. This is percentage of change in the size of the blocking events in the 2 data sets, summer, winter, the 3 sectors of the Northern Hemisphere and the whole Southern Hemisphere. And we see that basically there is this robust increase in the size of the blocking events in the Northern Hemisphere summer. In the Southern Hemisphere summer, there's basically no change. And in the winter, again, there is an increase in the size, though it's smaller, and the models don't agree as much. So after finding these results, there were a few things we could try to do, look at the implications for the change in the size of the heat waves or the mixing lengths. But we decided to actually take a step back and ask a more fundamental question, which is what sets the size of the blocking events. As you know, there have been a lot of papers about what sets the size of the synaptic eddies in the mid-latitudes, starting from work in the 60s with QG and a lot of work on with the idealized GCMs. And these studies basically pointed out to the importance of the Rossby deformation radius, lambda, and the Rein's scale in setting the size of the synaptic eddies. So when they started this work, we thought it just would be a month of work and one of these two would be the answer. So to find the scaling for the size of the blocking events, we built a model hierarchy. I already showed you some results from the large ensemble. And so to derive the scaling law, we went to like a simplest model in our hierarchy, which is the two-layer QG model. And these are the equations for the model. Probably most of you are familiar with these equations. I'm showing them here to point out that there are 7 parameters that you need to pick to define the system. And these are basically the lambda, which is the deformation radius. There are 2 time scales, tau, for radiation and for surface drag. There is beta, u, this is the speed of the jet, and sigma, this is basically the width of the Barthelinic region. And also there is the length of the domain, which is related to the radius of the planet. Now, to derive the scaling law, we used a systematic dimensional analysis technique called the Buckingham-Pi theorem that has been around for a very long time. And so in Buckingham-Pi, basically, first you list your parameters. So there are 7 parameters here, and they have 2 fundamental dimensions, time and length. And Buckingham-Pi says that basically with 5 dimensionless numbers, these are called pi groups, you can fully describe this system. So to do that, we choose a characteristic length scale. Here we chose lambda, a time scale. This is what we chose. And basically it says that if you are now interested in a new variable, like an area of the blocking events, the dimensionless area can be represented this way. So each of these variables in the brackets, these are dimensionless. For example, this is dimensionless radius of the planet. This is dimensionless width of the Barthelinic region. And then, so these are basically here, these exponents A, B, C, D, F are unknown. But we can determine them by either doing experiments in the lab or doing simulations. And here we just did simulations. So basically what we did, we fix all these 4 other pi groups. We change each of them for over an order of magnitude, like in uniform intervals. We did like 10 simulations for each. We calculated the average area of the blocking events. We fit a curve. We found this exponent. And we repeated these, and we found all these numbers. If you're not familiar with Buckingham-Pi, it's something that's widely used in fluid mechanics and especially engineering applications. For example, this is how they scale the measurements of like lift and drag in a wind tunnel to the actual object. So next time you fly a plane, this is basically how they estimated lift and drag. And it used to be that if something was used to design airplanes, it was of the highest standard. Maybe not anymore, but the method is very powerful. So, and it hasn't been used a lot in climate science, and I think there are 3 reasons for that. One is, in a GCM, there would be too many parameters, so you will get a lot of pi groups, and it would be hard to interpret it. Also, in a GCM, it can be hard to change like one parameter by like order of magnitude. The model can go unstable, or you might get unphysical results. And then there is a 3rd reason. I'll mention it later. But anyway, we did this. This is the scaling law we found. So we can now plot area versus the prediction of the scaling law. There are around 50 data points here, and you see that they all basically fall in one line. So we have a scaling law that works very well in QG, but the problem is that some of these parameters are not easy to diagnose from data. Like if you go to ERA5 or CMAP data, it may not be hard to just find a single number that we can assign to like time scales for radiation or surface friction or the width of the Barthelinic region. So we thought that, and I think this is the 3rd reason that Buckingham-Pi hasn't been used a lot, because climate science is a little different from like engineering design. So we thought about rewriting this scaling law in terms of variables that we are more familiar with and we understand them in terms of dynamics. For example, one is the Rein's scale that, as you know, is defined based on EKE or RMS velocity. So we basically repeated the whole process and derived a scaling law for the Rein's scale. We also thought that the width of the jet can be important. So notice that the width of the jet is different from sigma, which is just the width of the Barthelinic region. And in fact, when we derive a scaling law, you see that W depends on things more than just sigma. We also thought that Q scale can be important. So Q scale, this is the wavelength of a stationary Rossby wave. So if I set the phase speed to 0 in the dispersion relation, I get a length scale out of that. It looks like the Rein's scale, except that here, this is the mean speed of the jet rather than the RMS velocity. And so we derived a scaling law for the Q scale as well. Now, if you look at these numbers carefully for a while, you will see that, and in the paper we have uncertainties on all of these, you see that you can actually reproduce this scaling law just simply by multiplying this one and this one, and then plus this factor here. So we found that basically the size of the blocking events depends on the width of the jet, the core scale, and then this big dependence on the radius of the planet and the deformation radius. One thing that's very useful about this equation is that notice that you can get information about the statistics of the blocking events based on just information from the mean circulation. So this could be the seasonal mean or the annual mean or the decadal mean. So you don't need daily data or anything like that. And I think this can be useful to, for example, get information from paleo data. Okay, so we again tested this in the QG. Again, the same thing. You see that the new scaling law also works well. So the next question is, would it work in a GCM? So we took the Held-Suarez dry model, and in this model, we can change medial temperature difference, the time scale of the damping of momentum and temperature. And again, we can do like around 30 simulations. And again, you see that the scaling law works pretty well. All these 30 data points almost fall on one line. When delta T becomes pretty high, there's some deviation. So the next question is, would this work in the large ensemble simulations? So now again, showing you the results from the large ensemble simulations, we can go and diagnose the area as we did before. So here, these two numbers here are from the two data sets we had. We can also diagnose the change in the width and the core scale, and then you can get the prediction from the scaling law. So the first thing we see is that actually over the North Atlantic, the scaling law doesn't work, and it gets the wrong value and the wrong sign. But also in this region, the two models actually significantly disagree on even how the widths of the jet would change. But after that, it works pretty well. For example, over the North Pacific, 4%, 10%, these are the diagnosed change in the area from the model, and these are the predictions from the scaling law. Again, 4%, 5%, 3.5, 2.6, 2.5. Again, scaling law derived from QG, it actually works all the way to the large ensemble simulations. Then we looked at the summer, and in summer, the scaling law actually doesn't work at all. And in the summer, we found it very difficult to measure the width of the jet just based on those simple geometric metric that we had. Even in some cases, we really just gave up on calculating the width of the jet. So we started thinking about, well, why the scaling law works so well in winter and and doesn't work at all in summer. So it must be because of a process that is missing from our dry QG test case, but it would directly affect the blocking dynamics. So if it affects the blocking characteristics by changing the mean flow, then that would be captured by the scaling law. However, if there is something that directly affects the blocking dynamics, then, and it's missing from the QG, we are not going to get that through the scaling law. And of course, there's been really nice work by Stefan Fall and some of you in this room, for example, about the importance of latent heating. So we thought that could be something that we are missing. So we added the idealized moist GCM to our hierarchy based on MIMA. So in MIMA, we can change the CO2 concentration from like 75 to 1200 ppm. And again, do this experiment. There is a seasonal cycle, so we can look at winter and summer again. And again, we see that the scaling law works so well in winter, but not in summer. So this suggests that moisture really could be a factor in why the scaling law doesn't work in summer. But we thought about was to go back and redo everything from in a moist QG model and see whether we can get a correction to the scaling law. But also, it is possible that part of the problem in summer comes from the fact that the jet profile is more complicated. So we need better metrics for the width of the jet. And we thought about looking at definitions that are more based on the dynamics, like where the critical layers are and things like that. But we didn't continue that work because Ibrahim really wanted to look at the duration. So we left this for future work. So to look at how the duration of the blocking events would change, again, we followed the same hierarchy, except that now we also had the CSM2 large ensemble. And we look at two indices based on the anomaly and the reversal. Now, in these simulations, the mean speed of the jet changes under RCP 8.5. For example, in the summer, there's around a 20% slowdown in the jet speed. It's very clear in CSM2. Not so clear in the GFDL model because of what's going on in the North Atlantic. But some people might look at this and say, well, the jet is slowing down. We are going to get more blocking events, probably longer lasting blocking events. So longer heat waves, more impactful heat waves. So we thought to test the first part, which is to see how the duration of the blocking events would change in these simulations. And here are the results. So again, summer, winter, 3 sectors of the Northern Hemisphere. This is just lens 2 versus the GFDL. CSM1 also, like the results are very similar. So these are the numbers here are the average durations of the long blocking events, the one lasting for more than 10 days, in the current and future simulations. And you see that basically the numbers are very similar. So if you do a statistical test, statistically, there is no significant change between these numbers. And if you do this for all blocking events, same conclusion. If you just look at the shear index, same. And in fact, there have been a number of other studies that also found in CMEP 3 and 5, that the average duration of the blocking events don't change with climate change. So again, to understand what's going on, we went back to the model hierarchy, and we did some simulations with the dry model and with MIMA. In the dry model, we changed the meridional temperature difference over a wide range, and in MIMA, again, we changed CO2 from 75 to 1200 ppm. And I'm not showing the results here, but as you can imagine, the circulation changes significantly. Like the mean speed of the change changes significantly, for example, when you change these numbers over this wide range. But the average duration of the blocking events remains pretty similar. So here everything is normalized by the average duration in the control run, and the shading is uncertainty, but you see that actually the duration doesn't change. So to further investigate this, we decided to go to even a simpler model, the 1D traffic jam model, which is probably the simplest conceptual model that we have for blocking events. And Navarro already talked about this, but just as a reminder, so here A is the finite amplitude wave activity. So if A becomes large and persistent, basically you have a blocking event. It depends on the term here that is like an advection term, uref. This is some reference velocity of the jet. There's a nonlinear feedback term here, and S is basically the transient eddy forcing on the wave activity. And this model, as Navarro mentioned, has been derived in Nakamura and Huang's paper. And Navarro's group has since then done some really nice work in using this model and changing these parameters and looking at how the variability of the blocking events would be affected. So here we use that to look at how the duration of the blocking events will change. So the first thing we did, we fixed everything and we only changed this reference velocity of the jet. So if we increase this uref, the speed of the jet would increase and the blocking duration would decrease, as many people might expect. But also we know that with climate change, not just the speed of the jet would change, but also the eddy forcing can change. So we did another experiment. Here we fixed everything except that we changed the eddy forcing. So here, when this S increases, the speed of the jet decreases, but also we see that the blocking duration decreases. So now we have a slower jet, but also shorter blocking events, opposite of this one. But also we know that the change in UREF and S, they're actually related. For example, they can both depend on the meridional temperature difference. So we went to the dry model and we diagnosed UREF and S, and we fit a curve. And we put that parameterization into the 1D model. So now the 1D model only has one null, and that's the UREF. So now, in these experiments, we increase UREF, S changes proportionally. The speed of the jet actually increases, but we see that the blocking duration remains the same. So again, very similar to what we found in the idealized and comprehensive models. So basically it says that if you account for this change, the proportional change in the mean speed of the change of the jet and the eddy feedback, actually the duration of the blocking events would remain the same. Now, in terms of implication, we think one implication is that the increase in the duration of future mid-latitude heat waves is actually not directly related to dynamics, at least as far as the duration of the blocking events is concerned. So it has to be due to thermodynamics. And in fact, just a couple of years ago, when we were doing this work, Dave Thompson's group published a paper, and they looked at all sorts of different kind of analysis in a hierarchy of models, and they also concluded that the increase in the duration of future heat waves can be mainly explained by thermodynamics. And they pointed out that the major source of uncertainty in their analysis is that we don't know how the duration of the blocking events would change. So our work sort of filled this gap. I should say that, so Ibrahim graduated, and there's still a number of sensitivity analysis that we need to do, so we haven't submitted this paper yet, but hopefully we can get those done and submit this work. So our work only looked at how the duration of the blocking events would change. But again, the relationship between the duration of the blocks and the duration of the heat waves may not be something very straightforward. Again, I want to remind you of Packard's work and his work on looking at the relationship between the frequency of the blocks and the heat waves, and he found that to change. Also, I want to point out this really nice paper by Yi Zhang and Bill Booth that came out last year, and they found that actually convective instability sets the maximum temperature of the mid-latitude heat waves. And the way that I interpret this is that the decay phase of the heat wave and the decay phase of the blocking events may not be actually that related to each other. So it basically says that it's not just the duration of the blocking events that would determine the duration of the heat wave. So I think, again, like looking at this kind of work and like the kind of stuff we did here in looking at the dynamics, connecting them could be like an exciting area of research. In the next few minutes that I have, I want to also highlight this other paper that Ibrahim wrote, looking at how the structure and the intensity of the blocking events can change with climate change. So this is a paper that's mainly based on doing composite analysis in ERA 5 and the same model hierarchy that I mentioned before. We did some analysis of the budget of the temperature tendency equation. And we basically reported a number of findings in this paper. Just to highlight a few, so we found that latent heating plays an important role in setting the 3D structure of the blocking events. For example, it produces a westward tilt in the 3D structure. We found the vertical structure, the vertical wind structure of the blocking events actually not to be so simple. It's not just a simple substance under the anticyclone, and it could be more complicated. And we think this is important because in this paper, we found by doing this budget analysis that the adiabatic warming always plays a leading order role in setting the temperature anomaly at the surface. So as you can imagine, the structure and the amplitude of the vertical wind is very important for the temperature anomaly. The other thing we found was that in some cases, in some areas, in some seasons, under climate change, actually the response in the change in the blocking intensity and the temperature anomaly after we remove just the mean warming actually may not have the same sign. So the blocking events might weaken, but at the surface, the temperature anomaly might still increase. And of course, this is all based on models, and they're all like the land parameterizations and the land atmosphere feedback parameterizations. But again, this is something we found and I thought could be interesting. So we didn't explain a lot of things in this paper. We just reported some observations, but I hope it can motivate some future work in our group and in other groups. So to wrap up, again, I think there are a lot of characteristics of the blocking events beyond just frequency that we should think about. And I think now we have a pretty good model and data hierarchy to look at some of these questions. I think especially the large ensemble simulations that have daily or sub-daily data, like the ones that NCAR provides, I think they are very valuable in studying blocking events. We can get good signal to noise ratio. And then on the other end of the hierarchy, like a model like the boundary traffic jam model is very valuable in looking at the dynamics. Developing a scaling laws for the characteristics of the blocking events, as well as for the characteristics of the extreme events like heat wave. I think those can be useful. Again, you can get information about the change in the statistics of the blocking events only based on changes in the mean properties of the circulation, which might be easier to constrain from simulations and also from theory. We actually did some work on finding a scaling law for the duration, but it took a long time, and at some point we stopped. Developing a scaling laws with Buckingham Pi can actually be slow, and I think this is one area that machine learning can be useful to accelerate this. And in fact, there are already a number of papers about using machine learning to do Buckingham Pi analysis. They could be useful. As already mentioned several times in this workshop, I think developing metrics that connect the characteristics of the blocking events and the extreme events like the heat waves, I think that's something to think about more, and also try to develop integrated conceptual models that really couple the upper levels and the surface. I think that's something that can help a lot in better understanding how blocking events and the extreme events can change with climate change. So with that, I stop here and looking forward to your questions.
Great. Thank you very much, Pedram, for a really wonderful talk with lots of interesting stuff. So next up, we have Ziming Chen. He's going to tell us a bit more about the Pacific Heat Dome, I think.
Good morning, ladies and gentlemen. My name is Ziming Chen, and thank you for giving me this opportunity, and thank all the co-authors in this work. Today, I would like to report our recent work on how climate change would increase the likelihood of the occurrence of the heat dome-like stationary waves over the Pacific Northwest. And at first, what is the heat dome-like stationary wave? It is a high pressure or anticyclonic circulation, acts like a cap or dome, which would trap heat at surface and favor the formation of heat events. For example, as mentioned in Professor Parandam's talk, at the end of June in 2021, a very strong heat dome stationary wave emerged over the Pacific Northwest, leading to a 2-week-long heat event over the Pacific Northwest. And almost the entire Pacific Northwest have suffered from a unprecedented 10-day-long heat waves. Given it is important to predict or project the occurrence of the heat events, understanding the future changes of the heat dome stationary wave is very important. Besides, a much stronger enhancement in the heat dome stationary wave can be seen over the Pacific Northwest compared to other mid-low latitude regions. This figure shows the future changes in the eddy geopotential height at the 500 millibar. And the white stippling denotes a robust change across 26 CMIP6 models. And although the stationary wave circulation may be projected to weaken in the tropics or subtropics in the summertime, the stationary wave circulation may be varied in the mid-latitude. In addition, such robust increase in probability or intensity of the heat dome-like stationary wave can only be found in the boreal summer, while there is not robust change in other seasons. Normally, the summertime background state would be relatively weak and far away from the tropics, which would affect the declination from the remote forcing and the response in the mid-latitude. So in this talk, we mainly focus on what forcings are expected to add the greatest influence on the projected changes in the heat dome-like stationary wave over the Pacific Northwest. At first, to quantify the intensity of the heat dome stationary wave and the cyclonic circulation over the Pacific Northwest and reveal the climate impacts, we show the future changes of the heat dome and the cyclonic circulation at the end of the 21st century. And this figure, we show the projected changes of the eddy meridional winds at the end of the 21st century. And we will define the index based on it. A robust and a cyclonic circulation can be seen over the Pacific Northwest. And we defined a dipole index as the difference in the eddy meridional winds between the western and eastern flanks of the anticyclonic circulation. To link the heat dome with the heat extremes, we regress the summertime detrained daily maximum temperature onto the dipole index. And we can see that a strong heat dome and a cyclonic circulation generally will lead to a higher increase in the daily maximum temperature in the future projection. And similar pattern can also be seen in the observation. And based on this dipole index, we can see significantly increasing trends in the reanalysis and the historical simulation of CMIP6 models. And the dipole index would continue to increasing in the future projection. At the end of the 21st century, the heat dome and the cyclonic circulation would expected to enhance by about 95% under the high emission scenario. And when it comes to the forcing, we have discussed a lot yesterday. Normally, the stationary wave arise or could be maintained by the zonal asymmetries of the atmospheric diabatic heating, heat or momentum fluxes from the transient eddies and the topography. Besides, the mean state will also affect significantly for the characteristics or location of the stationary wave. In contrast, in the future projection, the projected changes of the winter time stationary wave is mainly dominated by the diabatic heating anomaly, while the mean state changes will also make pronounced impacts on the projected changes in the winter time stationary wave. And we would use a similar framework to investigate the projected changes of the summertime stationary wave based on the stationary wave model. We calculate the basic state and the forcings based on the daily output data of CMIP6 models. But due to the limitation of daily output data, we could only use 14 CMIP6 models to calculate the forcings. And by prescribing the present-day three-dimensional basic state as the initial condition, the model was run for 100 days with the time average performed over 30 to 100 days, driven by the diabatic heating, transient divergence, transient vorticity. And here we have not regarded the basic state as one of the forcings, because the basic state may be altered by these forcings, and this forcing may also interact with the basic state. To figure out the dominant forcing, we further design 3 single forcing sensitivity runs. To account for the potential interaction among forcings and to avoid the long activity, we keep the intrinsic forcing as the historical conditions in its sensitivity run. For example, in the diabatic heating run, the diabatic heating in the present-day climate will be used, while the other two forcings are in the future projection. And the single forcing response is defining as the difference between the all forcing run and the sensitivity run. And these panels show the projected changes of the eddy meridional winds projected by CMIP6 multimodal ensemble and the response simulated by the stationary wave model. And generally, the stationary wave model can capture the future enhancement of the heat dome and the cyclonic circulation, but the response over part of the North American is too weak. Besides, the simulation skill is better in the lower troposphere compared to that in the upper level. And our experiment design can reasonably capture the future enhancement of the heat dome stationary wave because of using the 3D basic state, three-dimensional basic state. We have compared the results shown here against those prescribed by the zonal wind basic state and found that the simulation prescribed by the zonal basic state could not reasonably capture the future enhancement of the summertime and the cyclonic circulation over the Pacific Northwest. And we further design 3 sensitivity runs to figure out the dominant forcing. And this figure shows the response in the all forcing run and the contribution from 3 single forcings and the contribution from the nonlinear effect. The nonlinear effect is defined as the difference between the all forcing run and the sum of 3 single forcing runs. The diabatic heating dominates the future enhancement of the and the cyclonic future enhancement of the heat dome and the cyclonic circulation, while the vorticity partly compensates the contribution from the diabatic heating. Given the significant impact from the diabatic heating, it is important to isolate the dominant sources. We further conduct experiments driven by the diabatic heating from different broad regions. And the diabatic heating over the tropical Pacific emerges as the predominant factor for the aforementioned stationary wave featured in the upper level, while the diabatic heating from other regions only contribute secondary. And next, we will ask, how could a tropical forcing affect the heat dome and the cyclonic circulation enhancements in the future projection? Normally, a tropical forcing would affect or change the Rossby wave source in the upper level and trigger a telekinetic wave trend, which will propagate to the mid-latitude. And for now, we have figured out the linkage between the future enhancement of the heat dome and the cyclonic circulation over the Pacific Northwest and the forcing over the tropical Pacific. And next, we will focus on the physical pathway. And at first, in the present-day climate, a high stationary zonal wave number tongue can be seen in the tropical northeastern Pacific. And under the changing climate, the stationary zonal wave number is projected to increase over the United States. If we regard the high stationary zonal wave number as a waveguide, the waveguide, the extent of the waveguide would expand under the changing climates. It would favor a more northwards propagation of the Rossby wave train. And this figure shows the Rossby wave ray paths sourced from the tropical northeastern Pacific, where the high stationary zonal wave honk locates. And the wave paths in the future projection in yellow propagates much northwards to the Pacific Northwest. In addition to the waveguide expansion, the Rossby wave source in the tropics is also projected to enhance in the future projection. This figure shows the projected changes of the diabatic heating in the entire troposphere and the divergence wind at the 200 millibar. And we can see an increase in the equatorial Eastern Pacific and a decrease in the tropical northeastern Pacific in the diabatic heating will result in a easterly and westerly divergence flow over the tropical northeastern Pacific, giving rise to a positive divergence anomaly. Since the Rossby wave source is associated with the divergence flow and the absolute vorticity, a positive divergence anomaly would lead to a stronger Rossby wave source over the tropical northeastern Pacific in the future projection. And this is the schematic diagram of the underlying mechanism that links the tropical forcing to the future enhancement of the heat dome and the cyclonic circulation over the Pacific Northwest. At first, due to the El Nino-like warming pattern, the Rossby wave source in the upper level will be enhanced. Besides, the extent of the waveguides will expand in the future projection. As a result, a more northward propagate of the activity flux can be formed under the changing climates over the Pacific coast of the United States, which would propagate a northward propagation of the Rossby wave train into and feed into the Pacific Northwest. And due to the more wave activity flux feeds into the Pacific Northwest, it will help to build up the heat dome and the cyclonic circulation there. And so the heat dome and the cyclonic circulation will enhance by about 95% under the high emission scenario. And our results mainly based on a linear framework. And we also conduct a series of experiments based on a fully nonlinear model, GFDL, Joint Dynamic Core, to verify the proposed mechanism driven by the global or tropical diabatic heating. And we got similar conclusions. And besides, our work mainly focused on the mean state changes. And I have read a couple visualized posters in these few days. And one of the posters have checked the results by using the real analysis. And specifically, this poster from Shekali also found a waveguide expand in the real analysis due to the diabatic heating in the tropics. And I'm very happy to see that. And thank you for all. Thank you for the attention. I'm happy to answer any question. This paper was published in the MPJ Climate and Atmospheric Science. Thank you.
Great. Thank you very much, Tiffany, for a really lovely talk. I'm looking forward to getting back to Europe a little bit faster this evening. So our final talk is Andrew Winters, who's going to tell us about jet superposition.
Awesome. Thanks, Tim, and thanks to all the organizers. It's been a really interesting couple of days. This talk here approaches a lot of what Tiffany was talking about from maybe a little bit more of a synoptic context in terms of trying to understand sort of the, let's say, trends and changes in the type of a synoptic evolution that might be conducive to the occurrence of these really intense jet streaks that we might see, let's say, in a future climate, as Tiffany was alluding to. For this particular work, I want to acknowledge Clary Ryer, who contributed to trying to understand a little bit more some of the relationships between these extremes and what it might mean for a future climate. So in terms of these polar subtropical jet superpositions, we're basically trying to describe an environment in which the polar or eddy-driven jet farther to the north will merge with the subtropical jet farther to the south to create a more robust synoptic environment. So from a conceptual standpoint, these jet superpositions are typically characterized by the remote production of a cyclonic PV anomaly at high latitudes with a polar jet streak typically located on the equatorward flank of these cyclonic PV anomalies. And then farther equatorward, we have these tropical anticyclonic potential vorticity anomalies with a subtropical jet streak typically located on the poleward flank of those anomalies. And these generally are indicative of a thermodynamic environment that generally is characterized by weaker upper tropospheric static stability, especially as they move towards mid-latitudes relative to the mean. And so if you take a cross-section through a typically separate polar and subtropical jet stream, you often see a structure that looks like this in an idealized sense on the top right, where that yellow contour represents the structure of the dynamic tropopause, the red contours are your potential temperature, and then the shaded gray contours represent your wind speed. So you see two separate steps in sort of the height of the dynamic tropopause there, with each jet generally residing within one of those particular breaks in the tropopause height. As required by the thermal wind relationship, each one of those jets also has requisite baroclinicity both above and below the jet core. So then you can imagine if some sort of confluent flow pattern sets up so as to allow the horizontal juxtaposition of these two PV anomalies, the result is a rapid acceleration of jet wind speeds in between, where those two sort of circulations induced by those PV anomalies are constructively additive. When you get that sort of acceleration of wind speeds, you also have a consolidation of the pole to equator baroclinicity into a much sort of smaller meridional contrast region. And that creates an environment that's perhaps a little bit more conducive to high impact weather. And you can imagine that blocking could be one of these types of environments that allows for these two separate jet streams and sort of flows or streams of the jet to become meridionally or sort of horizontally juxtaposed here in this particular case. And so if you take a cross section through these particular jet streaks here, rather than seeing that sort of two-step structure that we saw before, you have a single steep tropopause wall there in the presence of that anomalously strong jet streak. You have that rapid increase in wind speeds and essentially that consolidation of the pole to equator baroclinicity into that really narrow zone of contrast. And so this sets up an environment synoptically that is particularly conducive to high impact weather in terms of an ingredient-based standpoint. And so to highlight that potential for high impact weather, what we found from some of our work within the last couple of years is that there is generally this higher potential for high impact weather in conjunction with these mergers of the polar and subtropical jet streams. So what's shown here in this scatter plot is the location of surface cyclones relative to sort of the jet maximum wind speed when these superpositions occur. You can see that depending on where the cyclone is, there's differences in the intensity of that particular cyclone, with most of those cyclones generally situated or clustered in that left jet exit region of the jet streak, synoptically where you'd expect them to. But what we find is that cyclones that develop in conjunction with these jet streaks tend to be close to sort of 3/4 of a standard deviation stronger than your average surface cyclone, which is statistically significant. And we find that over a synoptic scale area in the vicinity of these superpositions, the 10-meter wind speeds generally are within the top 5th percentile for roughly 2/3 of these jet superposition cases. When we look at the potential for extreme precipitation, we find that depending on the AR algorithm you use, that between 54 and 84% of these superpositions are associated with an atmospheric river in close proximity, with most of those atmospheric rivers generally being located downstream of sort of where that jet maximum wind speed is, which is represented by the yellow dot there. And similar to intense wind speeds, we find that also roughly 2/3 of those jet superposition cases also feature 24-hour accumulated precipitation values that rank in the top 5% over a large scale area. So you're really seeing an environment that is translating to the high impact weather occurrences at the surface. And what we find is generally those events that occur closer to the east coast of North America or the Gulf of Mexico generally are those that have those extremes associated with them. If that merger occurs, let's say, over the Intermountain West, we generally don't see those linkages to high impact near surface weather. So the processes, though, that facilitate the development of these superpositions really vary based on the location at which these superpositions occur. And so what we've done as part of prior work is sort of partition these superpositions into a bunch of different archetypes. One at the top left represents more of a polar dominant type of situation where you can imagine the polar jet is really doing a lot of the work to meet the subtropical jet at its latitude. And then we have two more subtropical dominant type of cases, which is sort of the converse where the subtropical jet is really doing a lot of the work to meet the polar jet near its climatological latitude. And we split those subtropical dominant cases into an eastern and a western case because we found that the frequency distribution really sort of featured a bimodal distribution either on the west coast of North America and on the east coast of North America. So with these general archetypes in mind, one thing that I want to sort of center this discussion on is that ultimately the processes that facilitate this superposition occurring is dependent on sort of the type of event you're looking at. And the entire goal of this superposition process is to facilitate some combination of activities that allows for the tropopause structure to essentially be deformed from the two-step structure shown here into that single steep tropopause wall. And a couple of these processes can include just the equatorward transport of high PV air. So through some type of blocking pattern, perhaps you can have those polar cyclonic PV anomalies being dragged down from high latitudes to meet the subtropical jet. You can have, let's say, intense latent heating and convection equatorward of the subtropical jet. That sort of irritational outflow with that convection and the diabatic heating can drive that tropopause break poleward of the subtropical jet farther poleward to meet the polar jet. And then you can also set up favorable ageostrophic circulations in the vicinity of these jets so as to facilitate subsidence in that intermediate tropopause step, so kind of dragging that PV down the isentropes between those two individual jet structures. We find for the subtropical dominant cases that the role of latent heating is really dominant. So when we look at sort of future changes here, keeping an eye on that, especially some of the things that Tiffany was talking about, that idea of latent heating really being an important factor to driving those subtropical dominant cases may play a role when we look at some of these future climate perspectives. So this idea of sort of reforming the tropopause is sort of enshrined in the literature under this term foldogenesis. How do you create one of these tropopause structures? And that can arise through this combination of both horizontal and vertical motions in the context of the tropopause. This work sort of takes it a step further and says, let's add in a second tropopause break and understand how this is really occurring. So when we think about what this means for a future climate, I do want to introduce this idea here from Manny and Hegland, who looked at reanalysis trends in the positions of both the polar and subtropical jets. And you'll notice over North America in general that there's a tendency perhaps for the jets to get closer together in terms of their spacing over the continent and maybe a little bit farther apart over the Western Atlantic. Similarly, some of the work by John Martin has suggested that both the polar and subtropical jets, in terms of that core isotel that corresponds to the PV waveguide with each jet, is getting wavier in reanalysis products as well, moving towards the future. And so you can imagine that increased waviness just may introduce more opportunities for those jets to become superposed or merged together under this particular trend. And so let's take a look at what this might mean for future changes in these superpositions. And what we've done is basically look for instances in which the location of the two PVU surface at either 315 Kelvin or 310 Kelvin, depending on which reanalysis product you're using, is, let's say, vertically stacked with the position of the two PVU contour at that higher potential temperature surface, typically corresponding to the subtropical jet. So the potential temperature contours are generally chosen to represent those that are characteristics of each jet during the cool season. In the contours, that's showing the frequency of jet superpositions. You'll notice there's a lot more in the ERA 5 because we're looking at sort of, let's say, an atmospheric column that has a different sort of difference in potential temperatures there, which I think is leading to just more identifications there. But qualitatively, you're seeing the same identifications of superpositions in the same spot, which is encouraging between the reanalysis products. And then what's shown in the shading is whether you have an increase or decrease in the frequency of those superpositions during the last 20 years of the reanalysis period relative to, say, 1979 to 1998. And all of the reanalysis products agree generally in a decrease over sort of the Southwest US and somewhat of an increase, say, over more of the Southeast US, generally in a spot where you might, let's say, have a greater thermodynamic environment to facilitate, let's say, high impact weather in conjunction with these jet mergers. I also want to highlight, it's a little bit tough to see over the North Atlantic, but there's a very slight increase there. That's a bit of foreshadowing with what we see in the future climate. And then a little bit of a decrease in the reanalysis products off the West Coast where we see those Western subtropical dominant superpositions. And so to finish off here, this is looking at future changes in jet superposition. So what we've done is take the CESM large ensemble and the 10 high resolution and 6 hourly members where we have 6 hourly data within that ensemble. And we look at the change in jet superposition frequency between 1979 to 2014 relative to what we see in the last 35 years of sort of that simulation period. And what you see in the black contours is the ensemble mean jet superposition frequency during the historical period. We're using the 315 and 350 Kelvin isotopes to identify the superpositions. And this is very preliminary, but you'll notice there's a little bit something wonky going on over the Western US in terms of the frequencies there, which I think might have to do with the choice of potential temperature contours. But overall, what you're seeing in the shading there is whether there's an increase in the frequency of these jet superpositions in the late stage periods of the 21st century relative to the early part. And then the stippling indicates where 8 of those 10 members agree on the sign of the change. And so ultimately, you're seeing somewhat of a decrease over North America in the climate models, perhaps at odds with what some of the reanalysis products are showing, and a dramatic increase, say, over the Western and sort of generally North Atlantic in general, which may suggest more of an extended, elongated jet within that particular sector, perhaps agreeing with sort of the generally lack of blocking activity there or decrease from some of the climate model simulations as we've discussed. In terms of future changes, though, across the entire North American domain, we find that these mergers between the jets are projected to decrease during the winter season months. But we find that overall, the wind speeds associated with these superpositions, either at the 350 Kelvin or 315 Kelvin isotope, generally are increasing relative to what we see in the historical period, suggesting a stronger jet that may result from either stronger baroclinicity within the region, but also that effect Tiffany was talking about, that stronger, let's say, meridional moisture gradient might be playing a factor there to sort of that increase we're seeing in sort of the wind speeds associated with these superpositions. And then in terms of bringing this back to blocking, I do want to highlight the study from Davini and Andrea in terms of sort of future change or sort of representations of sort of how blocking has changed within reanalyses versus observations. There's certainly this disagreement between observations and, let's say, what we're seeing in the climate models or reanalyses, which sort of complicates some of the interpretation here. But in terms of what we're seeing with superpositions, I think dynamically within the model, there's perhaps a little bit of some agreement here where if you get some of these superpositions occurring, let's say that are more eastern subtropical dominant in their flavor, those jets may extend more zonally across the North Atlantic subsequently, and let's say create an environment that subsequently is not perhaps as conducive to blocking over the Greenland area, sort of consistent with that positive NAO type pattern. So just to summarize here, I just really want to pose some questions here, thinking about sort of these jet superpositions as it's really sort of a work in progress. We really want to understand sort of what are these processes responsible for changes in superpositions. We think latent heating is a big part of that. We want to tease out that climate change influence a little bit more, as well as what the connection might be to high impact weather in the future. And then I think there's still an outstanding question of really how do jet superpositions either result from blocking events, with what frequency, let's say, or with what frequency do jet superpositions serve as an antecedent environment to that blocking developing farther downstream, say with an explosive cyclone that develops in conjunction with these features. So with that, I'll stop there and yeah, entertain any questions during the panel discussion.
Right, brilliant. Thanks, Andrea. Another great talk. So yeah, if we could have all the speakers back up to the front, maybe Tiffany back on screen if possible. Great, brilliant. I can see queues forming. Let's start with the slides since it's more over there.
Hello. Yeah, thank you for the awesome talks and sending us home in the right way. I have two questions. The first is for Pedram, and maybe Tim can chime in on this. So do you trust the climate change projections? And then I guess if you do, for the decrease in blocking for winter and summer, what's your take on what's driving them? And do you think it's the same kind of mechanisms? And then for Ziming, is what you're saying about the increase in the stationary wave compatible with projected decreases in blocking?
Well, for the change in frequency, I mean, as Tim's paper showed, there are just a lot of uncertainties, and the signal is as big as the bias in the model. But also, I think when we talk about the change in the frequency, it really depends on how the algorithm of the blocking detection work. If you are looking at the number of blocked grid points versus the number of blocking events, right? So if you're looking at the number of grid points, like that can be affected by actually just changing the size of the blocking events, right? And then defining what is a blocking episode or event, right, itself can be complicated. So I think overall it's just complicated. There's a huge uncertainty. Changing that size, it was pretty robust, the numbers that we showed in our paper. It's just a little easier to like define size, and it was a very robust signal. And the change in duration, again, we found it to be overall robust and didn't depend so much on the definition of the block. And other people also found it just in the CMAP. But I think with frequency, I think Tim's paper is very comprehensive in terms of the state of the understanding.
I mean, maybe just a quick thing as well. I think Pedram, your talk showed us that we don't really understand summer blocking on its own well enough, and the controls on it well enough to know if the models are doing right or not. So there was a question for Ziming in there as well, I think, wasn't there?
Oh, yeah, thank you for the question. And actually, when I come to the workshop, when I see some posters or talk, I also very surprised that many results may be contradict for my results, which is increasing in the probability of the heat dome stationary wave. But I want to say it may be due to the difference of the definition of the stationary wave of the blocking. And in my talk, I quantified the probability of the heat dome stationary wave mainly based on the dipole index. And the dipole index, and how I calculated it, I used the daily data to calculate whether this day will occur the dipole pattern. If so, I would think it is the occurrence of the heat dome and stationary wave. So in other words, I have no account for other many factors. For example, the duration, the consistencies, and other factors. So my conclusion in the increasing in the probability maybe have a the definition dependencies or something like that. So thank you.
Can I add something to the answer to this question? So for the size, that's another thing about having a scaling law. So in the paper, we looked at the increase in the size, how much of it comes from the change in the bits, how much of it comes from the change in the core scale. And it was to some degree dependent on the region we looked at, but if you have a scaling law, then you can kind of break it apart.
Yeah, my question's for Tiffany, but just thanks everyone for your talks today. Really interesting. Tiffany, I'm trying to follow the method with the waviness and like looking at each grid point and meridional wind values. How does that alone correspond to looking at changes in waves? Like, don't you need some sort of spatial pattern linking the meridional wind anomalies together to like look at wave changes?
So yeah, thanks for the question. I think that the definition of waviness in the community is certainly not agreed upon, but we certainly know that without, for example, Rossby waves, if we had an angular momentum conserving jet, it would be purely just zonal. So we know that meridional flow is connected to Rossby waves. I think that is clear. In our analysis, we weren't distinguishing the type. Certainly you could do low pass, high pass filter to get at that. We've looked at spatial structure, it's I think very consistent. If you just look at the, for example, mean of our distribution, you see the stationary wave pattern. So I think it's all in there. And the question is, how much do we want to disentangle it? I think for us, the next step is certainly regions and to see how this plays out. And then I think we'll get to some degree at your question about wavelength, let's say.
Okay, so it's kind of like a bulk measure of waviness, like the activity, the meridional. Like, yeah, okay, I got it. Thank you.
Hi, Tiffany, this is Gang Chen. So I have a question for you. So you started with performance, aggregation, precipitation, and then I think Paul also look at spatial pattern of those changes, and it turned out the spatial pattern is dominated by dynamic, not necessarily thermodynamics. So I wonder if you have looked at spatial pattern of this kind of wind speed changes, and do you see a uniform increase, or do you see some spatial structure changes? I think you mentioned stationary waves, so do you see like pattern like that?
So yeah, implicit in this kind of terminology I'm using is that it's related to the spatial structure you already have to some degree. And so when we look, for example, at fast winds over CONUS, so over North America, we do see that kind of connection to the patterns we have. I mean, the mean is just an average of the distribution itself, but certainly, showing in different regions and different seasons, something that we're actively doing, but I can confidently say that the behavior is very clear in CONUS in North America, and we're continuing to unravel all of the implications of this result that, as you say, is very bulk average, but purposely so to kind of get at the leading order and then, of course, unravel the dimensionality.
Yeah, I agree. Like when you average, even for precipitation, it's mostly thermodynamic. But when you look at spatial pattern, and at least for precipitation, most people will say there are a lot of regional circulation changes, and that turned to be more important than thermodynamic.
So maybe what I'll say is what the results suggest is that you can't really separate thermodynamics and dynamics.
Sure.
Our results are showing that the dynamic response is a function of the thermodynamic response. That's what the multiplicative increase is telling us. And so I don't really know how to think about dynamic versus thermodynamic anymore when they are actually intimately connected.
Yeah, that's fair. I have a related question. So if you look at some event with really strong wind, do you know what kind of weather pattern that's associated with? Look to me, you may be just talking about like front line with really strong wind, and have you had a look into those weather pattern?
Yeah, I mean, these are daily snapshots, right? So just like I showed on my intro slide, the daily snapshot of a very fast moving North Atlantic jet stream. How that relates to superpositions or other things like Andrew talks about, we haven't dug into, but it's certainly interesting and something that we're eager to do.
Thank you.
I'll just add in anecdotally too, from a synoptic standpoint, and digging around with some of these situations where, say, the jet wind speeds get above 100 meters per second or so at 250 millibars. it's really difficult to get these situations anywhere other than some type of upper tropospheric ridge. You'll have that sort of super geostrophic flow over the top of the ridge, and oftentimes those sort of really strong jets really are situated in that particular environment. And so I think that the connection to sort of the waviness that Tiffany was talking about, I think is a central component to this, because I think you need the waviness dynamically so that that sort of ageostrophic component added on to the geostrophic flow gives you those extremely intense wind speeds.
Right, thanks very much. Let's do one online for now. So let's go with Prachi, I think, who was first, and then we'll go back to the room.
Yeah, hi. I firstly thank you to all the speakers for a really informative talk. So I have two questions. First one for Andrew. I wonder if you have checked the connection of your superimposed subtropical jet and its location with changes in the planetary stationary wave or any particular mode of variability or any large-scale SST patterns that we have heard about today earlier. Yeah, if you can share some thoughts on that or if you plan to look at it. And the second question is for Tiffany. It's again related to the previous question. So extreme events tend to be very regional, and it's so the large scale constraint is really cool to see that the winds follow these moisture or precipitation multiplicative increase. Do you have any thoughts how to tackle the regional relationship? What processes could be important for increasing or decreasing or modification of these relationships between moisture and dynamics?
I'll start with that first question is a really good one. We haven't explicitly explored sort of the way the jet superposition frequency varies as a function of let's say some of those stationary modes or large scale teleconnection patterns. I think it would be a really interesting question. I think my mind first goes to like an ENSO type pattern. During an ENSO type pattern, you tend to have that really strong subtropical jet, and anecdotally this winter has certainly been one where the subtropical jet has been awfully strong over the southern parts of North America this year. And that same sort of El Nino pattern also sets up sort of ridging on the West Coast in the branch of the polar jet. And so at least a hypothesis might be that, say, an El Nino pattern might set up more of those environments for some of those jet superpositions, say, over eastern North America than we might see during a La Nina period. But I think it's certainly only a hypothesis, but digging into that would be really interesting.
Yeah, that's a great start for my response too. I think that everything that we've done can be done. It's actually calculated at individual grid points. As Gang said, that's how they started for precipitation. We're kind of taking that as a first step. And just as they did for precipitation extremes, one can unravel regionally where these different things, how they interplay with one another. But again, I just want to highlight, there's no sense in which we're going to have a dynamic versus thermodynamic. I mean, essentially the thermodynamics are in the driver's seat here. And to me, that's a good sign because that's the thing we have the most confidence in. Clausius-Clapeyron, that has what led to so much progress, not only in extremes, but hydrological cycle changes. And I think it's a really good thing if we can start to make these connections between Clausius-Clapeyron and dynamics, because it will lead to more robustness, I think, in our understanding.
Right, thank you. We'll do two more in the room. So Hilla first, and then we'll go back online.
Okay, hi. Question, and thanks for your talks, great. Question for Andrew. We've seen in the previous session that the jet is becoming more zonal, or there's this zonalization of the jet in the North Atlantic. How is this related to jet merges and the superposition between the jet? And do you think, yeah, how much of it is multi-decadal variability?
Yeah, that's a good question. I think in terms of sort of the zonalization of the jet, I think one thing maybe I didn't emphasize in my talk too much is we're talking when these superpositions occur as sort of a smaller subset of the typical days in a winter, where these types of superpositions strictly only happen maybe a handful of times during a typical cool season. But when they do, let's say over the Atlantic, it certainly will be one of those situations where you're likely projecting strongly onto that positive NAO type pattern. And so if that positive NAO pattern, in a sense that we're seeing maybe in sort of a zonalization of the jet moving forward, is a function of, let's say, some more tropical influence that's, let's say, driving, let's say, ridge amplification over the region, but you still have the same synoptic scale dynamics that are driving sort of troughing within the region, you're just sort of setting up that dipole of a positive and negative PV anomaly horizontally through that particular mechanism. So I think that there likely is some sort of similar story there that's maybe in the background state, setting up an environment that's more conducive to this event occurring, let's say, more often than it would in a future, or than in the historical climate in the Atlantic. But as far as multi-decadal, I think that's another really good question. I think that could be really interesting to explore as another component. I will say, at least in terms of some of the trends, I tried splitting up comparison of periods that were smaller in duration and saw the same consistency of spatial trends too. So it is robust of that future minus historical change, depending on sort of what that sort of length of time you choose is for the end of 21st century versus historical.
Hi, this is Paul Liketh from Portland State, and thank you everyone for a really great session. My question is for Ziming. So the structure of the heat dome and the ridge that was associated with the heat wave in the Northwest in 2021 was kind of more of a cooler season type of pattern. It was pretty late in the year for getting such an amplified ridge and amplified block. In fact, we looked for analogs, historical analogs of similar patterns, and I think all of them, if not, it was most of them, all occurred before late June when this one occurred. So it's kind of one of the things that made this event so remarkable was that you had a cooler season type of setup with maximum insulation, allowing things to get really hot, and it was record breaking on top of that. So I was a little surprised in that sense to see the June, July, August aggregated results showing projected increase in such features. I have two questions. One is, did you look at how that broke down by season, since like these do happen, or not by season, but within the season, these do happen in June. They're more common earlier. In fact, I should say that the block that affected the Western US just the past week or so looked more like the heat dome than types of things that you see in July and August, for example. So is this dependent on the month? And if not, did you look at like individual events that made up the statistics in June and August? They look kind of heat dome-like in this sense, or are they a little different?
Okay, just confirm your question is whether I have seen whether there is a seasonal dependence, right?
Yeah, like within the season. So is it increased predominantly earlier in the season when these are more common, or your results showing they're showing up later in the season where they're less common?
Yeah, I have checked the monthly probability change or something like that at first. So which means that I have checked every month, and such enhancements can mainly occur in the July and August, if I remember right. I can show you the results later and the plot. Although I only show the seasonal mean in my talk.
Okay. And then just a really quick part two to that. If you remove the zonal mean 500 millibar height in July and August, you get kind of a sort of stationary ridge feature over the interior west.
Yeah.
And in projections under warming, that feature amplifies northward. Is it possible that's playing a role, or even what's showing up as opposed to like transient blocks and heat domes, or is it like all in the mix?
Just confirm. You asked me the shift or something like that. Could you repeat that again? I'm sorry.
Yeah. So there's like a climatological ridge-like feature over the interior west, and under projections of warming that expands northward and westward, it kind of sets up and what looks like an increase in ridging where you're showing this increase in heat domes. And I was just wondering if those are related, or maybe it's more of a climatological shift as opposed to a change in transients.
Oh yeah. Thank you for the question. For the Pacific Northwest, I'm not sure about that, but in the subtropics, I have quantify the shift, and we did see a very clear shift, eastward shift. Yeah, but in the Pacific Northwest, I can say I cannot say. I'm not sure. I'm sorry.
Okay, thanks very much. So let's go to James Ryan online, and perhaps in the interest of time, people could kind of restrain themselves to one question each for this last bit. Thanks.
Hi. All right. I'll just ask one question then. Andrew, and great talks to everyone, by the way. My question is about the sort of different results between superposition in reanalysis and in model projections. I was wondering, at least for the opposite signs in the southeast, if some of that decrease that we're seeing between today and the end of the century, I wonder if it's possible that that's more of just a reversion to the mean, at least in the southeast, and if there's a role that decadal variability may be playing in that. So, like, I'm wondering if it's reasonable that there isn't actually a large decrease between, say, a few decades ago to the end of the century for superposition in the southeast, to kind of like rectify sort of the results from both.
Yeah, that's a great point. I think that's entirely a potential hypothesis that could sort of resolve some of that dichotomy there. I think I feel pretty robust about the signal in the reanalysis being real from just the agreement of different reanalysis products, but then also in coincidence with some of the prior work that suggests the jets are trending closer to one another, just increasing that opportunity. But I think you're exactly right. Going to decadal variability is a potential explanation there for what we're seeing in the southeast. I think could be really interesting because it really is the only spot in the reanalysis that seems to not agree with what the climate models are suggesting. But at the same time, it could be a type of situation similar to what we're seeing with some of the blocking frequencies in let's say that region where we have differences in what we're seeing in the reanalysis versus what the trends in the climate models are suggesting as a whole too. So it could be something where seeing how things play out over the next couple of decades here moving into the future may reaffirm how things are changing there. But I think it could be a really interesting question, maybe best addressed through some type of idealized modeling approach where you can get some of those longer, more decadal aspects of variability in there and look at sort of the jet response over, say, multiple, let's say centuries, for example, to try and tease that out.
Thanks so much. I have another question, but I'll just email that to you for the sake of time. Thanks.
Great, thanks. I think Noureddine was pretty next.
And a question for Andrea. Very basic question. Is there any correlation between the speed of the jet after the merger and the extreme event that might be associated with it? My thinking is that if you have a confluence jet, then that will drive the forward Asia-Pacific circulation that sets up as overturning. Therefore, that might introduce some storm genesis to the south. If that's the case.
That's a great question. We haven't explicitly explored, say, how strong the jet wind speeds are in conjunction with the high impact events. One thing we did see is that, and it might be worth to look at anomalies instead for the different events, but what we saw for events in our paper that led to high impact weather, the jet wind speed was actually weaker than the null events, but that was the total wind speed. And what we saw was there was a greater propensity for high impact weather to develop in association with jet superpositions during the shoulder seasons rather than the heart of the winter. So I think what we're seeing in terms of difference in wind speeds in the composite is more a reflection of the seasonal climatology and not necessarily that wind speeds are weaker during high impact events. It may in fact be actually just anomalously more strong in the shoulder seasons. But I think the big player for the high impact weather is probably more so the more potent thermodynamic environment that resides during the shoulder seasons when those events do have a better propensity to lead to high impact weather. Good question.
So I just have a question for Pedram. So you said that when you change the transient eddies and fix, like you referenced something, you found that block duration is going to be decreasing. I'm just interested, have you ever thought of like, looking at the latitudinal extent maybe? Because the thing is, we spot that the short-term or let's say short-lived anticyclones are more often found over lower latitudes, often referred as low latitude blocking. I was just interested whether these transient eddies could be like, the reason behind decrease in the duration of what. So.
Yeah, that's a good point. So in the 1D model, it's one-dimensional just in longitudes. And the reason that actually changing that S has such a big impact on the duration is actually it changes the variance. But in terms of what you are talking about, we haven't done that, and I think that would be something interesting to look at, like the results that we showed. We basically just look at each sector, but I think breaking this down into different latitudes, I think that could be nice. And with the large ensembles, I think there's probably enough examples of blocking events to do that. Yeah, that's an interesting suggestion.
Thanks.
Thanks.
Can I ask one more quick?
And then quickly.
Yeah, I just have a question for Andrew. Maybe I've missed, I don't know, but I spot that you found that superposition events would be decreasing in lens 2 as well. So over the southwestern part of US. So I was just interested whether, like, what's your opinion on like blocking possibility over that region, and whether there is any, there may be any relationship with superposition of both jets and maybe blocking. That's the thing.
Yeah, that's a really good question. And I don't have a good answer to it, but I think that maybe just, thinking off the top of my head, a type of situation that, let's say, maybe you're still maintaining blocking there, but not, let's say, producing a superposition could be more of a Rex block type situation where you've got sort of the separate sort of high and low centers in the block sort of situated right on top of each other meridionally. You may not necessarily in that scenario get the two streams to merge as appropriately in that scenario as you might with sort of the character of like an anticyclonic or cyclonic wave break. So linking in sort of the structure of blocks and the flavors of blocks to the occurrence of these events is, I think, a really good question. And I would imagine that there's likely certain flavors of blocks that increase the probability of superpositions more than others. That would be a really interesting research project, especially if you trend it to the future characteristics too.
Thank you. Thank you so much. Thanks.
Okay, great. So let's wrap up there. Really great session. Maybe what we should do is thank, again, maybe not just these speakers, but all the speakers throughout the whole workshop for being really incredible at sticking to time. I don't think I've ever been to a workshop like this where everyone's been so disciplined. So well done, everyone. Okay, it seems like we might have critical mass now. So thank you all for being very persistent. Your block-like persistence has got you to the end of the meeting. This is the final session. We have our final bit of maybe not Eddie feedback, but a bit of kind of breakout group feedback now. And we'll go through this as normal, starting with group 1. So does someone from group 1 want to come up? Yeah.
Yeah, we had a nice wide-ranging discussion. When we did our drawings, I guess the most common features that came up are the upstream cyclone and warm conveyor belt potentially intensifying with more moisture, greater latent heat release, and in terms of impacts, heavier precipitation due to increasing water vapor in the future climate. Yeah, so we identified a number of open questions for the theory of blocking in a changing climate. So how might diabatic effects increase in a warmer climate? How would that impact block formation, for example? How will blocks impact storm, in particular tropical cyclone steering? How might surface fluxes and downward long-wave radiation change in the center of a block? So with decreasing baroclinicity in the Northern Hemisphere, does waviness increase or decrease? Probably depends on how you define waviness and quantify it. How will jet structure and wave breaking types change in a warmer climate? That's a big open question. And how will this relate to changes in blocking? And how does the lifetime of blocks change in a warmer climate? How does this vary regionally? And finally, how will the AMOC changes that we saw in a one of the talks, impact blocks over the North Atlantic. Yeah, so what Earth system components need improvement? Well, we need to better understand dynamics for the end of blocking. So we talk a lot about block onset and duration. An important aspect of that is what causes the block to terminate. And there's maybe a lack of research on processes resulting in block termination. Air-sea interactions, stratospheric impacts. We haven't heard much about those in this workshop, and those are indeed important in some cases. In practice, what is needed to produce a better forecast? There's a discussion of how we bridge the gap between theory and practical forecasting in this realm. Can we study failed forecasts or forecast busts to learn about relevant processes for blocking? I think that's something Emerson brought up and it was really insightful. Are models getting the magnitude of internal variability correct? That's an open question. And then what sets the stationary waves in the first place? It's boundary forcing like snow cover, also dynamics, resonance, baroclinic conversion, eddy interactions, and interactions with diabatic heating. So yeah, that's a really nicely written summary of our discussion. Thank you, Kevin, for writing that up.
Yeah, thank you. For our group, we talked about how summer and winter blockings might change under climate change. In summer, we talked about how intense precipitation, usually mainly related to moisture availability, could provide latent heating and intensify blockings. This intense precipitation could also happen downstream because of the relationship of blocking and cyclones downstream. A larger area of blockings is expected, even though decline in the frequency is highly uncertain, except for some regions such as like the North Atlantic. With regards to impacts, we talked about, together with especially drier soil and enhanced surface temperature, that we could expect more intensified heat waves and even wildfire risk under the ridge. In winter, again, we talked about this upstream latent heating that could intensify blocking, especially related to atmospheric rivers coming from the equatorial region. Again, this warm air transport upstream could lead to sea ice retreat by this poleward heat transport. And again, we also expect downstream cold air outbreaks, even though we might expect these to be less intense under global warming. And can I get the next slide up? So on open questions, we talked about uncertainties in model representation of processes and also uncertainties in our wide range of metrics that we have for blockings. We talked about how land atmosphere feedbacks are represented in our models and especially how we need to understand those better in a changing climate. We talked about how certain studies focus on regional changes while others focus on global changes, and we need some kind of agreement between those to have a better understanding. We also talked about how large number of metrics could lead to some uncertainty, but also could be useful if we have some better understanding of how to use certain metrics for different aspects or to study different aspects of blocking. On the interactions with other components, we talked about diabatic heating and tropical teleconnections, of course, but specifically we talked about how we need to disentangle the changes in the processes themselves and the changes in the teleconnections that are actually linking the blocking with those other components of the Earth. In improvements, we talked about model resolution a lot. We talked about how model resolution can affect process representations, such as, for instance, El Nino, Southern Oscillation, even how it can improve model physics, like the worm conveyor belt. We talked about how this resolution also could lead to an improvement in land features, such as orography, that can significantly impact blockings. And finally, we didn't have much to say about the Europe-America schism, but we talked about the weather-climate schism. So we talked about how climate as a large discipline addresses different aspects such as modeling, scales, impact, while education usually focuses on weather forecast and specifically impacts. And these two can increase the gap between the two disciplines. However, there is this silver lining in that there is this opportunity to collaborate more specifically based on this climate and weather seamless integration of the modeling aspect of both disciplines. So yeah, that's about it. Thanks.
Yeah, so we talked in our drawings, I invited people to put uncertainty kind of estimates on things, and so we ended up with a lot of uncertainty on a lot of what might change in the future. But we did all agree that thermodynamically, the warming and increased moisture, increased latent heat release is going to be something that we need to think about quite a lot. Yeah, and then Jan made this beautiful figure of the tug of war between the Arctic amplification warming versus tropical warming, which is going to have competing effects on the background potential vorticity gradient, which then will influence how blocks are formed. So yeah, and I liked his representation as sort of a yin-yang there. That was about it for images. Is anything? Yeah. And then we talked a lot about unknowns and actions to address that, thinking about gaps. The sea ice response and generally the polar responses in both the Arctic and Antarctic, where we're a bit observation limited, which then limits our capability of modeling all of these. But we know that there's going to be both an impact of blocks on the Arctic and the mass balance of ice sheets, and also then those Arctic processes feeding back on the blocks. Another big theme was increased representation or improved representation of convective processes, which are important in the tropics for getting teleconnections right, as well as the in situ cloud and latent heat release processes near the block itself. So just improving those characteristics and models, really important. Yeah, we realized that wasn't much discussion about forecasts of blocks, even though that seems to be motivating a good amount of why our group was here. And we know that people study predictability of blocks. It just wasn't really a focus in this workshop. So we were just wondering, all this climate representation of blocking, how is that similar or different to how we can improve forecasts of blocks? And of course, there's a range of timescales that we make forecasts on that aren't necessarily the same as climate. Also, the fringe seasons, spring and fall, are highly understudied compared to winter and summer. Is that justified or not? Maybe it is a bit, because you can get from summer and winter, you can get kind of the extremes, and then the fringe seasons represent some sort of evolution, but we all felt like we'd like to know more about blocking in those seasons. And yeah, kind of the European American thing, we were all kind of like, we don't really know if we feel that division, but there are some differences in the impacts of blocking. Blocks are kind of sit directly over Europe more than being in the Pacific and affecting North America downstream. So the kind of differences in the phenomenon and where they're located relative to where we're all living can motivate different interests in what we think about for blocking. So anything you wanted to add?
I think that mostly covers everything. Yeah, I think just going back to the very beginning, there was, we all sort of noticed the important dynamics, but yeah, just the too many question marks for any sort of certainty in terms of projections on climate change. And I think those interactions are really key and make things even more complicated. So lots of work there for future climate.
We organize this kind of talks together, and so there are the main three questions that we found important in our discussions and got some results. The first one was about the open questions. So firstly, we started to discuss about a kind of classic questions. So when the temperature gradient decreases with Arctic amplification, whether it would be like the cold air advected is cold air advected decreases, or because the temperature gradient decreases, there is a thermal wind balance and got wavier jets, and then the block related waves will be amplified. And the second one, we got how well the jet bias and tropical SST errors combine to affect the representation of blockings now and in climate change, which I think is the part that we got the greatest disagreements in our discussion, saying that because we tend to believe that the jet is kind of decided by the tropical SST, mostly controlled by the tropical SSTs, and however, the observed tropical SST cooling trend is not well represented in our models, and what happens about that. And the third point is we need to consider the effect of multi-decadal variabilities and global warming together, considering the blockings. Or if we believe that most of variabilities will change with global warming, leads to another complex question. And finally, we got one possible solution for understanding such different possibilities as a storyline approach that we could suppose the most likely scenarios and got some results based on the different scenarios. And the second question is how to improve the representation of blockings in models. And we got, firstly, we have a discussion about what is most responsible for model errors, which is kind of close to yesterday's discussion. And it covers clouds, convections, moistures, and model resolutions, no matter horizontal, vertical, or even time resolution, which is expensive, and the dry dynamics that affects the blockings. And then of course, the couplings, especially the coupling between the ocean and the atmosphere, is that well captured. And then one thing that Christine mentioned is that this kind of problems doesn't go with climate change, but amplify it because we tune the climate models based on current state. And the final one is the knowledge gaps between modes of variability and the blockings. Need to consider the combined effect of modes and with rather than consider one single mode about blockings, and if models can well represent this kind of interaction. And the final point is in contrast to using climate models, we could consider S2S focused database to explore and dig more knowledge from this kind of database. Yeah.
Hi, everyone. Here representing the online group. I had a nice chat with them. So it's, hybrid group for the day. So some of the things that we discussed that were either kind of understudied or improvements are needed to better simulate blocking. Things that are understudied include like impact of subgrid mountain drag scheme, convection scheme, and other parameterizations. Kind of how are these sources of bias leading to biases in blocking. One thing that was asked is what grid scale is needed in the first place in order to get blocking. As mentioned before, the impact of the stratosphere, this is something that's a bit understudied, and I think part of the reason is because it's not well simulated, but is important for blocking. We talked about the SNAPC project that's undergoing that may help answer some of those questions where they nudge, for example, sudden stratospheric warming events, and that may help start to answer some of these questions, but certainly not all questions. And something that is certainly needed, improvements to better get things like blocking frequencies, tropical impacts, but also teleconnections are not well simulated. And also their interactions are also important if we want to get an accurate representation of blocking frequency. Some challenges with blocking in a changing climate. Going back to tropical teleconnections, some of those changes are really uncertain. So for example, there's a possibility that the teleconnections associated with the MJO will actually weaken, despite the fact that it is expected that the MJO will become stronger, and that has to do with changes to the mean static stability. So there's a lot of things to consider, and that would impact MJO or all tropical teleconnection impacts on blocking, as well as predictability of blocking. Let's see. Blocking itself is also poorly simulated, so that adds a lot of uncertainty. to any blocking changes in a warmer climate, kind of as was discussed by the earlier groups. Regarding extremes, the question on extremes, so some things that could impact the ability for models to get the extremes associated with blocking. Precipitation itself is not well simulated, right? There's a lot of issues, especially with extreme precipitation. There's challenges with topography, land sea contrast, air sea interactions, things that could impact a wide variety of factors that make precipitation itself be poorly simulated. So this is going to have an impact on how well we're able to capture blocking impacts on extremes if we're not able to get those extremes in the first place. So something to think about. We also discussed some recommendations. One of the things we talked about deals with kind of this kind of continuing question on all of the blocking indices that we have. And one of the things we discussed is to think about blocking in a similar way that we think about ENSO, the El Niño Southern Oscillation. ENSO has a lot of diversity, right? We have East Pacific El Niño, Central Pacific El Niño, and so forth. And you can't capture ENSO diversity with only one index, and blocking may be similar. It may be that we cannot capture blocking, all the flavors and diversity of blocking with just one index. So one of the things that we discussed is that it may be helpful to think about blocking in kind of a similar way. I'm thinking about the diversity of blocking. And we also talked about like how it could help to specify a blocking name with the kind of type of block in the same way that when we're talking about East Pacific ENSO impacts, we would specify East Pacific or Central Pacific and so on. That way, whenever we see things like this index is showing an increase in blocking frequency over North Pacific, whereas this one's showing a decrease, it may be that it would be useful to know like, well, this type of block is increasing, but maybe this other type of block is decreasing, or maybe there's different biases associated with different flavors of blocking. So that's kind of a thought we had. We also thought it would be good to kind of examine the relative contribution of different modes of variability on different blocking regions and types. And lastly, thinking more about the climate change uncertainty and simulation of blocking, thinking about simple models or SOS models or a hierarchical approach, kind of better understand the impacts of model bias sources. So similar to the previous group discussed, we need model experiments or analysis in general to better understand how different impacts of like parameterization and things like that are impacting blocking in the first place. Thanks.
Great, brilliant, thank you. I think there are no more groups, probably, is that it? Great. So just thanks everyone for all your work in the breakout groups over the last few days. They've been really productive. It's, everyone's joined in and talked and shared things. It's been really wonderful. So, so thank you all for your, maybe give yourselves a round of applause for breaking out. Right, and now we hand over to our leaders for the finale.
All right, I first want to revisit our quiz. So you guys have some idea already? Well, first of all, if this particular cartoon looks familiar to you, if you ever taken like an introduction to atmosphere science, it's a hint, So, all right, I'll pause for a few seconds in case you have some. Yes, here we go. So this particular plot from Mike Wallace's book has this drawing, and this drawing dates back to 1991, when a great guy worked on his dissertation, I suppose. So Noboru Nakamura was the artist for that. Do you want to introduce to the background? When was that? And so this is the first drawing for blocking in a way. So that's kind of what we are trying to all do in colorful.
I feel a little sheepish about this, but Bramwald, when I was a postdoc at GFDL, asked me to draw something like this for his book, Physics of climate. So this original drawing was for his textbook. I think I still have copyright for this, so this has been recycled for a couple of times, and so this is probably the most profitable piece of my published work. Not profitable to me, but yeah, profitable. So thank you.
Let's thank Noboru for giving out the permission for using this. Importantly, we want to thank everyone here, both the virtual participants and in-person participants. You're all great, and I want to, in particular, thank for all of you who travel from all different countries, because I know some of you have to travel 24 hours in one way. That's incredibly, challenging. I can imagine that. So I appreciate from folks from all over the world. Hopefully we can get together in the future in similar venues. Also want to thank all the SOEC members, and you guys are doing a great job. The conference, the workshop has been very smooth, and I see a lot of great outcomes coming from it. And also session leaders and our earlier career and all the leaders and rapporteurs. Also want to thank for our sponsoring agencies and DOE, NOAA, and NSF. And in particular, I want to point out that for the support from NOAA, I think to my understanding, this is for the first time we receive both the climate office and also the weather office support. So this is a great opportunity for continuing this effort to mending this schism. And also, let's thank Alisa for the great job for putting all the stuff. Also thank Mike, who is overseeing everything from behind. And also let's thank Jessica and Sarah from UCAR for organizing the logistics and travel. For those of you who are early career, you're probably interacting with them for all the hotel and travel booking. And also thanks for Kelvin and Fletcher for our great in-house media support. So thank you all for the support. So this is a great thing because hybrid meeting is hard. We have people from all around the world, and we're doing everything very smoothly. I'm grateful for all of you. And this is the picture, and I think we will be able to share the picture with everyone right after this. I post some of the very colorful drawings here, and so I think we'll have more of them posted in the website in days to come. So I'll pause here for seconds for you to kind of digest and day 3 drawing. Pause here for a few seconds. And let's come back to this vote. So I'll leave for Jens for leading this, because I think you're thinking everything from the beginning. Okay, so thanks for all of you who cast your vote, and your voice matters. So yeah, and also thank Alicia for actually make a count for all the checks here. I'll go from the first one. This one is a little bit mixed bag. More would agree this is yes, and some would say no. Does any of you want to, iron your opinion regarding this one? I know this is really challenging because we don't have the time dimension here. So you have to use your imagination to, to envision what happened before and after. So, so yeah, what's in your mind? Want to share any thoughts? Well, we have top synopticians here. Can I invite Lance to give us an insight? Like, this is a map discussion.
All the way across the North Atlantic, so I would.
So cutoff is not quite your block.
Hey, Lance, do you mind going to the mic so the
virtual people can hear with your thoughts? Thank you.
My vote is no, because it's continuous flow all the way across the North Atlantic. But there's a cutoff flow there that maybe a day or two earlier that was part of a block. It's possible. Like, it might be the result of unblocking. That's just my 2 cents.
Anyone wants to defend for yes?
Yeah, I'll defend on yes, although I don't know because obviously we haven't actually calculated anything. But also I put this picture in, so I feel slightly guilty about this. Yeah, I said yes because it is, you know, it is a reversal of the flow. You know, the geopotential height reversal is there. So yeah, if it was persistent enough, then I would say yes.
Anyone wants to add more opinion? Or are we tied at this point? So let's move on to the next one. This seems like a overwhelmingly yes. And you know, we're thinking about the blocking MIP, you know, one of the really challenging thing, but very important thing coming from the discussion from here. And I would argue that for any of the index, that got to be a yes as well. So if not catching this, then we have to revise the index, right? Would I agree? And what about this one? So mostly no. And anyone wants to share your opinion, why you would think it's no, or why you actually think it is a block?
Actually, for me, it's just a guess. I assume it's the Berkeley structure. So, and maybe it's my bias. I thought blocking is relatively kind of a barotropic structure. It's very likely it's driven by some convective heating, in that area. So very similar kind of enhancement of the South Asian high. And also, where's the storm track? I always need the storm track or the jet as a reference. Another reason is this is a summer, right? If I remember correctly. Yeah, it's far, far north. No? It's winter. Okay. I'd be wrong.
Anyone wants to add? Pause here for a second. I know you guys are debating whether to support yes or no. All right, let's move on to the next one. Well, we have a great time yesterday. And for those of you who are still around, still have some pending plan for this afternoon, I encourage you guys to embrace the nature at Boulder. This is a great place, and I've always enjoyed my time at Boulder. Okay, this is the last slides, and thank you all for all the time. And yeah, let's conclude the workshop.
Right, I have 2 things to say. First is maybe just to kind of build up a little bit on those, the blocking quiz that we had just now. Is this a block? Isn't it a block? I guess one of the kind of reasons we did that is because a lot of these meetings, there's invariably a lot of discussion about blocking indices. Have we found the right metric for blocking? Which index should we be using? And I guess a lot of us have this feeling that maybe there's a huge diversity in the types of structures, and that actually the people, forget the indices, the people probably don't agree on what blocking is. And I guess we've kind of proved that in this workshop. There are some cases that are really clear, and everyone would say yes, this is the blocking. Other cases, people would the majority say no. But there's a lot of cases that are in between, and I think this is, maybe one of the things I've taken from this is we need to kind of embrace the diversity in blocking structures, and having, that's probably going to involve having more than one metric. So we can see where that goes, but I've certainly kind of learned something from that. Second thing, I don't know if anyone else was planning to say this, but we shouldn't leave without saying a huge thank you to our co-chairs, Pengfei and Zhang. I mean, this is really, it's been an incredible workshop. It's we've covered lots of ground, lots of different topics. Really great discussions, bringing lots of people together. And it really was the brainchild of these guys, and going through the effort of getting in the CLIVAR and other funding for it is really brilliant. So let's have a huge round of applause for these guys. And V is looming. I don't know why.
Yeah, so there's two things I want to mention. There's students in here, right? Students, do you mind standing up? So just a big round of applause for all the fantastic students. Wow, there's a lot of you. This is our future right here. So great job to all those students. And then one last thing, Deepti, can you stand up? So Deepti is hosting a heat wave workshop at Columbia University this July. I don't remember the dates, but the 10th through the 12th. So definitely be on the lookout for that. Thanks, everyone.